Okay, welcome again in this workshop on GANs for media content generation, which is initiated by AI4Media project, which is in general artificial intelligence for the society and the media industry. So the project started in the beginning of September, so we are just 1 month in the project duration out of the 4 years. Okay. So the overall vision for AI4Media is to become a center of excellence where technologies and are going to be developed and applied for the key sector of media, AI-related technologies, of course, maintaining values around artificial intelligence, where Europe and European Commission pays a lot of attention. So ethical and trustworthy AI will be embedded in our AI developments. And we, as we will discuss later, we plan to make the outcome beneficial not only for the, let's say, financial sector and part of media, but also for society in general. We just had our kickoff meeting, yesterday and the day before. We are 30 partners. In the kickoff meeting participated more than 80 participants, and we are very excited to have this project also official starting. Some key aspects of the project, as you will see here. So in the middle, in the center of this diagram are the R&D or research and innovation related activities. But apart from research and innovation, research and development, there are many other supporting activities. Like, for example, we plan to have a very strong training and doctoral studies program, which will try to, as I will also explain later, to gather similar relevant contributions from various organizations. We have also a program for involving external stakeholders through calls for funding external projects and research. So there will be open calls for participating in AI4Media related activities. And one important aspect of the project is that it is built around the use cases. So within the project, together with the industrial partners of the project, we plan to combine the modules that we develop in order to have prototypes and early products in the areas that I mentioned here, and we will see later. And there are other activities, other supporting activities, like, for example, this European Media AI Observatory, where first we will try to capture and monitor what is happening in the area of media and AI in Europe and in general. We also already building, and we will try to have strong connections with the AI4EU. You might know it. It's a European platform for Central European platform for AI, and we plan to make all these outcomes publicly available and accessible through a virtual center of excellence, which will be a portal available to everyone. Why media and what we consider media in AI4Media? Media is a key sector for society. As I mentioned, in general, it is about information and communication production and delivery. And in our project, we consider news and journalism as a key subsector, social media, entertainment, arts, gaming, and creativity. And as I mentioned before, apart from the economic value, we consider all this having important societal value, and today's workshop has a strong connection with these societal values, because if technologies are used in a responsible way, an ethical way, can be beneficial for many applications. But as we most probably will also see today, there are cases where where technology can be a threat to our democratic society, leading to polarization and crisis. Like, for example, these cases include bias in approaches, and of course use of technology, for example, for fake news generation. Regarding the overall research pillars in AI for media, just an overview here. Emerging AI paradigms focus on decentralized learning and AI on the edge. Fair, accountable, and transparent machine learning, robustness and privacy in AI, another very important key issue. In general, AI for multimedia content analysis and creation, involving activities like analysis, summarization, production, annotation, and so on. And as you might have seen so far, an important aspect of the project, human and society-centered AI technologies. And under this part, manipulation and synthetic content detection is corresponds to the more specific topic of our workshop today. As I mentioned, regarding trustworthy AI, one of the key aspects for our project is elimination of biases and veracity of content and information. So here, just to show you an example, we will see more of this later in the detections, an example of what manipulation and synthetic content detection in multimedia refers to. There are approaches regarding entire face synthesis, some specific attributes manipulation, identity swap, expression swap, and so on. And as this appears in content, in news that can affect public opinion, it is very important to detect these manipulations and inform journalists and readers about these manipulations, so they can consume content and news more responsibly. Some of the challenges that we try to address within AI4Media. So, for example, one issue is that in many cases, especially for AI projects, there is a focus on large centralized projects and infrastructures, and this leaves SMEs with limited funding and limited access to this infrastructure, to talent, which is usually attracted by such big projects and data. One reason why we tried to, let's say, support and work with the media sector is because it is a sector which is highly affected by the global situation. It's a highly globalized sector with high competition, where new solutions are for this sector, especially in Europe, to be able to compete with this international competition. And as I mentioned, due to misinformation, bias, and to other reasons, AI advances in this sector can be, instead of a benefit, a threat to society and democracy. And apart from R&D, a little bit in more detail, what we are doing regarding talents and SMEs in AI4Media in order to address, to an extent, the previous challenges. As I mentioned, we are building up an international AI doctoral academy, which will be a dense program of internships and secondments. and also, maybe more importantly, for external partners, a collaborative collaboration between various PhD programs. Furthermore, it will establish links to sectors beyond the media, and will try to have a participation both from academia and industry. And again, relevant to external partners, we are going to have this cascade funding program where SMEs, mostly coming from media sector or creative industries, will be able to co-develop technologies and applications with AI4Media, have access to talent from the doctoral academy, and be able to uptake cutting-edge R&D and have a quick transfer to the market. Here are the use cases where we have use cases around journalism and news, entertainment, creativity, social sciences, and humanities. And our overall vision is to mobilize and attract a large community and become a reference point for AI in the multimedia, media sectors, and beyond. So if you like to keep up with our progress and outcomes, you can visit the website and our social network accounts, and also register in today's event, so you are informed about our activities. Thank you very much for your attendance and for participating in this event. We are on time. We have 2-3 minutes for questions before we start with the next presentation. So if there are any questions regarding this introductory presentation, please raise your hand, and we can have time for 1-2 questions. Okay, it seems that we don't have any questions, so we can go on with Marta presentation. So Marta, I will stop sharing. You can share your presentation. Let me see also in Facebook if we have any comments there. No? Okay. Very nice. Okay, so we can go on. So it is a great pleasure to welcome and introduce Marta Mark to give the first invited talk in this workshop. Marta is a lead R&D engineer in BBC. She did her studies with the University of Zagreb in Croatia, and she did her PhD Queen Mary University, where I had the pleasure to meet her a long time ago. Then she was a postdoc also in Queen Mary and Surrey University, and now, as I mentioned, she has a key position in BBC, and she is also an honorary professor in Queen Mary University of London. Her research activities are around video coding and compression, and She has done, of course, tremendous amount of work in publishing, in organizing the events, getting recognized for her work, and so on. So, Marta, again, thank you very much for accepting our invitation and for being here. And we look forward to your presentation.
Yanis, thank you so much for such nice introduction, and especially for bringing your project to my attention and giving me this opportunity to learn more about the project and activities, which I think are just brilliant, and I'll definitely follow what you are doing. Also, thank you for giving me opportunity to share some of our recent work, because it looks like it really fits into several aspects of consortium's work. Before I start with technical parts, can I just, Yanis, ask you how much exactly time I have? I suppose 30 minutes plus 10 minutes for questions?
Yes, I think 30 plus 10 minutes will be okay.
All right, I think we have some delay. This is typically caused by my Wi-Fi at home. I have to apologize in advance if my family members come here and do
I think
children activity.
this is usual and expected nowadays. So the strange thing is not to happen.
All right, so let me start then.
Sure.
So basically, I work at the BBC, which is UK's public service broadcaster, and it's nearly 100 years old. In less than 2 years, we'll celebrate 100th anniversary. BBC content, and especially news, consumed all around the world. And we know that currently reach of the BBC various services is about 500 million people per week. This is thanks to providing news in more than 40 languages, but probably also the reason for such huge reach is that international news services rank first for trust and reliability. What is probably less obvious about the BBC is that it always relied on latest advances in tech to reach audiences. So in order just to reach 500 million people weekly, we need to take all advantage of all the possible ways digital platforms help us connect with those communities. We have a large group of engineers that works 24/7 in order to maintain that digital technology core element of reaching people. A small department in this engineering group is research and development, and this is where I work. Our job is slightly specific for the whole BBC because we are supposed to support BBC in long term to make sure basically that we can take advantage of all developments happening in broadcasting and other relevant technologies. So AI4Media work perfectly fits into what we are looking. Basically, to keep an eye on emerging technologies, we also engage deeply into fundamental research, and we dig deep into promising tools. We are about 200 engineers and scientists, and obviously we have to strongly rely on a number of partnerships, such as those funded by Horizon 2020 programs, where we work on various research topics. And now to my presentation. Basically, it will be around my particular specialism in visual data processing. So I'll talk about some of our recent work in that area. Today, we will hear talks that address various applications of deep learning, mainly GANs, or on visual content. In particular, I focus on two very specific aspects of how to predict pixels in two completely different scenarios. The first one is learning to predict color pixels using GANs, which is very challenging because of its ambiguity. For this specific task, we have a lot of freedom to add complexity, experiment, tweak the networks, and so on, as this colorization task is expected to be done offline. On the contrary, the second scenario will address video compression, traditional video compression, but enhanced with new deep learning modules. And that scenario targets real-time execution on user devices. So we need low complexity, robustness, no space for ambiguity. That part of the talk will not address GANs, but will demonstrate how we use interpretability and explainability of deep networks to predict pixels. So let me start with the first topic, video content enhancement. In the context of this talk, mainly refers to making pixels look better. And there are a few areas where deep learning can help, not only help, but provide currently state-of-the-art compared to traditional methods. It's much better. And these areas are, for example, denoising, artifact removal, color adjustment, and so on. So different layers of a deep convolutional network, which are the basic blocks of enhancement tools. In visual data enhancement comes from special is the whole presentation video that the beginning of the credit features contain more texts, more global features. Achieve. Just to show you briefly a successful application of convolutional deep network. All right, I'm getting some messages that there is no voice.
There is voice, but there are these delays and interruptions. But I think this is what we can do. We have the slides. Then it's becoming better, and so I don't know whether we can do anything else.
Yes, probably that video caused too much trouble. Hopefully, I will not have. I'll try to skip videos as much as possible. So basically, yeah, let me know. I get some messages. I can see them when There was someone suggested I should stop my video. Let me just leave it for now, and if there are problems again, let me know, and I'll stop it. So basically, all right, I'm asked to repeat the previous slide. I guess what I'm trying to say with the previous slide is that the key to visual data enhancement and processing with deep learning is the fact that we have ways to flexibly apply neural network with 2D convolutions, because they can capture features on various scales in spatial domain. And that slide was just an example of what actually computers see, and now it's up to us to figure out how to put that capability into delivering a useful tool. So I have a video here which I'll try not and just move to this one example, which is basically scenario that is very well known to many of you. And on the left-hand side, you can see upsampled video, simply upsampled by linear interpolation. And if you look carefully, you will see that it's blurred. On the right-hand side, you can see how video can look when neural network add details. Especially, you can see, for example, that letters around here are in much better, they have much better sharpness. And why I'm showing this result is we didn't use GANs here, although one could use. These results were obtained a few years back within one of our European collaborations, and they inspired us to keep learning about deep learning and its application in other broadcast and media scenarios which involved visual data. So let's move to image colorization, which is the main part of the talk today. Basically, first let's try to clarify, why do we need colorization of black and white videos? Lots of historical content simply doesn't have colors, but colorizing the frames manually is very time-consuming task. Even 40 years ago, 50 years nearly, attempts were made to colorize images with help of computers, so semi-automatic colorization. A lot has been improved in these 50 years, and some fascinating results can be obtained with modern semi-automatic approaches, such as shown here for restoration of World War I content recently. But there are also other semi-automatic techniques. For example, this example has an interesting tool which basically allows a person to indicate which colors should be used in each of the regions of an image, of the grayscale image, and then program automatically colorize the whole image. As you can see, results are very naturally colored images. Here's another example where a person doesn't have to manually select colors for each image region. Groups of 3 images, like for example here, I hope you can see my cursor, is you basically have black and white image, you have an example, and then using deep network, you can get automatic colorization this frame here. So a few examples are included here. Again, this method provides very realistic colorization results. However, this semi-automatic approaches still require expensive manual effort and artistic experience to achieve such nice acceptable results. Because of the cost associated with such semi-automatic approaches, we started looking at availability of end-to-end machine learning solutions for colorization. End-to-end means that basically they do not require any manual intervention. But what we found is that such approaches struggle to produce colorful images because it's very difficult to learn which colors to use where. So why is that the case? Let's say that all these colorful cars are used to train a network. And basically the larger the selection of training data is, it's more difficult to obtain later on colorful results. This is because traditional deep learning end-to-end methods use pixel differences, for example, L1 norm to train the network to colorize. And this results in, putting different colors together, ending up in something brownish, which is called the saturation effect. So this is an example of what would happen if we try to colorize this specific set. Let's say we have it black and white, we want to colorize it, we'll end up with very brownish images. Luckily, a couple of years ago, authors of Pix2Pix network, which is brilliant conditional GAN image-to-image translation network, also demonstrated that more colorful colorization of images is possible using this. Pix2Pix is powerful in various scenarios, but unfortunately in our experiments it did not deliver sufficiently colorful images. And we anyway decided to keep working on it because this basic framework, which is very applicable to various domains, can be specialized further for colorization tasks. So I'll try to now dig deeper into the colorization and our changes. The goal in our experimentation, in our work, was to basically obtain an efficient generator. In this case, this is this unit, which takes black and white image and produces colorized one. This is unit, it has encoder decoder with skip connections between mirrored layers, or in encoder and decoder stacks. So what is characteristic for Pix2Pix is that it uses GANs in conditional settings. So while GAN learns to generate model of data, this conditional GAN learns conditional generative model. And we condition the input with the input image to generate corresponding output image. This is the conditional part of it. And generally in GANs, both generator and discriminator compete against each other towards improving the performance during training. So basically, if we have here a generated image produced by generator, discriminator should recognize that this is a fake image. But if we give to the discriminator condition, we condition the discriminator on input image and give it corresponding real colorful image, it should be able to detect that it's a real image. And basically, the discriminator here all the time takes pairs of images. during training, obviously, generator learns to fool the discriminator and learns to produce fake images which are more and more close to reality. So the main message here is basically that both generator and discriminator take a black and white image as the input. So in order to get better results with GANs, it's usually very difficult to figure out how to stabilize them, how to make them produce something good. There is no let's say a magic recipe that helps always. So we experimented with various tools, and I will explain some of them. First of all, while Pix2Pix, our basic approach, our baseline uses batch normalization. We try to improve that because the batch normalization is used typically to accelerate training, and it means that the original network in all layers, in all of its layers, used internal mean to invariance of the batch to normalize each feature channel. Oops, let me go back. And specifically, this is very important for GANs because it stabilizes the learning process and prevents collapse of mode, which can happen if we poorly initialize the network. On the other hand, it is known that instance normalization enables learning of the features that are invariant to appearance changes. And basically, what we did is here and here replace batch normalization with instance normalization. Here we are closer to the pixels of a generated image. We use instance normalization. This restriction preserves content discrimination in deep layers because we still use batch normalization here, but brings benefits because it focuses on single instances. So basically in a batch, from the mini batch, we focus only on the single instance. The next improvement we made here is applying spectral normalization. This is basically regularization of weights on the discriminator side to prevent instabilities caused by unbounded gradients on discriminator side. And this helps us generalize the style changes of larger data sets so that variations in laws, in adversarial laws, do not prevent us from suddenly changing such laws and ending up in observing only L1 loss. So for example, here, normally we would get stuck with very large adversarial loss in the blue line. But then when we use either batch normalization or instance and batch normalization together with spatial normalization, we have better competition of generator and discriminator. And by doing this, we prevent observing only L1 loss. We keep taking into account adversarial loss, which is super important because looking on it, L1 loss would not produce colorful images. And the other challenge in colorization was to achieve precision in small areas and local details. So in Pix2Pix, actually, we have a single scale discriminator. It's Markovian patch GAN, which is fully convolutional. this enables discriminator to output probability maps based on input patches from the input domain. However, to boost colorfulness, one would use larger receptive fields of the original discriminator. However, this can lead in inference to various undesirable effects, such as blurry effects and tiling artifacts, very nasty color artifacts. So, better solution, which we found in other literature, is to use multi-scale discriminator, as it can tackle high-resolution image processing. In particular, we use 3 discriminators at different scales, and we are downscaling images by factor 2 and 4. As a result, we can take during training the 3 losses, discriminator losses, combine them, and then the network learns to also add some detailed color, different color in other regions. You can see in these examples here, a multi-scale discriminator is used in here, unlike here where the rest of the image is mostly green. So these are details are missing. This example is a video, so probably you will not hear me well, but I think it's yeah, worth trying to show it to you, because it nicely demonstrates how during training the prediction changes until the discriminator generator sort of stabilize, and how at the end for the black and white images we can obtain, using this trained generator, these colorful images, which are it was better, okay. Compared to ground truth, they're quite nice, although one might not agree that this beer looks very realistic. We released the source code of this, and you can obtain it. We are also continuing working on this internally, and with Dublin City University and with UPC in Barcelona. Basically moving from this approach of colorizing small images to adding more balanced loss, perceptual loss in the generator, and towards automatic consistent colorization of high resolution videos. How we evaluate the result? This is always a big question in GANs. And we followed an approach devised from observations that histograms of natural images, as you can see here, these are histograms of 2 color channels. If you see the blue line represents what the histogram would be for real images. And other lines are different colorization methods. So the basic method that we applied without all these adjustments hugely reduced the histograms. So closer the histograms are to the real value, they actually indicate more colorful images. These images do not have to have exactly the color of the ground truth, but are more colorful and therefore more realistic, which was missing in previous techniques. You can read more about this elsewhere, but I would like now to spend a little bit of time, because we don't have much. Maybe I'll try to go in for a couple of minutes into video compression. Mainly because I would like to introduce the concept of requirement for explainability and interpretability of AI. We here don't present end-to-end deep learning compression methods. Actually, we focus on how to enhance available, practical, widely implemented video coding standard with some machine learning. So before we go into investigating whether we can make the machine learning algorithms, especially deep learning algorithms, simple, faster, let's go here one step back and remind ourselves what actually is required in the delivery of content. Here we have a video, and then a video is of a high frame rate, which is indicated with this thick blue line. Before it's distributed to numerous devices here, it has to be compressed. So this block here represents compression. And if we, let's say, use standard solution here, the compression is not sufficient to reach, let's say, some devices, so we have, let's say, buffering here. So the idea of using AI in such video codec is to, like I put here, a black box which represents various AI tools, is to help reduce the bit rate further and enable these devices to receive the signal. The problem here, which we are now trying to solve, is that AI relies on something it learned, and we don't know often what it is. So we call it a black box. This is now a very hypothetical scenario where, because we don't understand, let's say, some border case of this AI, we can trigger undesirable scenarios where, for example, none of the receivers receive video. So to prevent this and to have more trust in these powerful AI technologies, we should aim at developing transparent boxes of AI, as I indicated here, the black box turned into the transparent box. And these boxes can be interpreted and their behavior can be explained so that the blackouts, let's say, are prevented. This transparency of AI boxes also brings another benefit, which is that once we know what AI has learned, we could potentially trim it and simplify it, make it light and more easily deployable. Such desirable forms of AI, I throughout my presentation, show with a gold star. So this is fully predictable learned model, which we can, as engineers, guarantee will not break the delivery chain. And in the rest of presentations, which I don't have time to show you, I'm explaining how various tools based on deep learning integrated into standard video codec can enhance compression, but are usually come with totally unusable runtimes, which is a big problem. And we don't know actually what they learn, if they can be simplified, they are too far from being practical. So we are trying to explain what is in these boxes, and we didn't have a method to do that from the literature. Literature typically focuses on a classification scenario, as demonstrated here. If user wants to, for example, know what sort of bird this is, then AI will tell what the what sort of bird it is and why this decision is made, and even may say why it's not something else. This doesn't work in a video codec. So we devised new ways to interpret compression tools and make them significantly less complex and explainable to users. Well, users are not members of audience, they are video coding engineers, so that they can reliably implement them into their systems. No time to go into details how we built this for fully connected layers, how we then used this to interpret and explain deep convolutional networks for interprediction, and also chroma prediction with attention models and convolutional and some other branches. Basically, we published all of that in our blog posts on website and papers, so you can have a look there and or contact me if you are interested to know more. The point is, the message is, there is no single way to use interpretability and explainability of a neural network, but we have to try and better understand what is happening in order to be responsible for what we are deploying. And here I included a few pointers for very, very interesting work that has been published recently on explainability of different networks. Finally, to conclude, I will not conclude about GANs, because I think today we have a much more to hear and learn. I conclude on use of AI in media, and basically it helps us hugely to innovate in very new ways in media sector, and we embraced this opportunity. However, this great tool has some negative consequences, such as excessive use of computational power, biases in related systems, and very often the transparency is missing, totally missing. So when designing or relying on systems which include learned components, good practice is to include people in the process who have very deep technical understanding of deployed machine learning, and to have practices of careful ethical selection of data for training. And as demonstrated through our video coding examples, for example, here in this presentation, interpretability and explainability is needed. It is an extra effort for each network, but understanding deeper brings additional benefits. So this is it. I would like just to highlight that examples of this research were achieved mostly in collaboration with wonderful teams from Queen Mary University of London and from Dublin City University, thanks to our national EPSRC funding and Horizon 2020 grants. This funding enabled me to assemble this amazing team who among other work, deliver all the results presented here. Thank you for your attention.
Thank you, Marta, very much for this very interesting presentation. It seems that we have to invite you also in the next event, because there was so much to show that you will need another presentation for all this work. Thank you very much. So yes, we have the first question comes from Ryan. I think it would be very, very nice. So, Roberto, please go ahead.
Hello, Marta.
Hi, Roberto.
Thank you for the presentation. That was very nice. I found interesting the approach to pixel colorization with GAN. My question is, do you think it is possible to combine semi-automatic approach with GAN? I mean, to suggest to the GAN a sort of color palette, something like a guided colorization, maybe in the form of ancillary data.
Yes, that's a very logical continuation of this work. I will give you one example. For example, we have lots of historic Doctor Who footage, black and white. No idea what the colors were. But apparently there are some photos of the filming set in color. So giving such palette to colorize video would be something that that we'll try to do, probably using GANs in some aspects, because we don't have the ground truth, right? So I think there is potential, and I wish the team was bigger to faster deliver results. But if you're interested to collaborate, we can definitely catch up later.
Thank you.
I'm expecting a video coding question from you.
You're right. I will think another question for the next meeting.
All right.
Thank you.
Okay, thank you very much. I think Professor Peters wanted to ask something, but now unfortunately the connection seems lost. We have also, okay, Professor Peters is back. Did you have a question, I think, to ask?
Yes, my question, Marta, is why do you need explainability and interpretability in your tasks, colorization or compression? You just do it and that's fine.
So let me give you one example. We've seen big compression gains obtained using super resolution networks applied for interpolation in pixels for motion compensation. Researchers train 10 different networks, find for which the coding gain results are the best. Why? Nobody knows. So what we try to figure out is what is so special in the training data and the network that this new tool enables that hasn't been observed by signal processing researchers for last 30 years, right? And what we find out is by analyzing the results and the features that these networks extract, how actually the interpolation works. The differences are so minor. And I also suspect that most of the gain doesn't come from the super smart deep learning, but from the fact that video coding standards had to reduce the accuracy of interpolation filters in order to make them faster. However, the deep learning approaches keep the accuracy, and they come up with filters that are very similar with to DCT bases used in traditional coding. So understanding that this network actually just has better approximation of DCT filter, that it learned better approximation of DCT filter, helps us understand why we have these gains and whether it's good to use this new tool or not in future.
So basically, you're thinking about scientific explainability.
Yes, yes. I will show you very briefly.
We have also other questions as well. So if we can see something about this and
so using explainability, fully explained predictions, we were able to, for each sub-pixel prediction, explain which samples from neighboring pixels contribute to interpolation of that pixel. This is to Yanis's question about explainability in video coding. And I will show you, I will send you a link to our demo on this and would very, very much appreciate feedback. I mean, this is, let's say, alternative approach to explainability. And we are very interested in, you know, how community comments on it.
very nice. Marta, you can paste the link in the chat window so also all participants can see it. And I think Lorenzo also had a question before Akis. So Lorenzo, yes, please.
Hi. Thank you for the very nice presentation. So I'm kind of curious since you have you see all these problems both from the industry point of view and from the academic point of view. So if you can comment on some of the drawbacks that is any of these used in production at BBC? And if you can comment at least on one of these things that you explained today, on what is the drawback in applying, you said something about computation, but I'm very curious if you can go a little bit in depth on this issue. So applying these techniques in production, what is done, what are you doing at the moment, and what cannot be done at the moment? Thank you.
Yes, I will try to. That's a very good question. I'll try to answer it, but you know, it's a very wide and very important topic. So I believe that we at the BBC, when getting technology from outside that is based on machine learning, we should be able to understand what the trained model does. We should be able to understand why are we where the sort of weak points and what are the strong points of specific technology. Of course, I mean, even a video codec that is 30 years old has, you know, its problems, and everything is fully explainable, but for specific content it will fail. I believe that everyone who tries to deploy machine learning solutions on mass scale, reaching many people, should be accountable for what is part of that technology. So in the past, we knew, you know, interpolation filters have these coefficients, so we can expect such signals. It might not work in some cases, but we understand what it is. However, ML solutions often come really as black boxes, and they can they can work on, you know, 100% of the test set, but in practice totally fail. And we want to prevent that.
Okay. Okay, thank you very much. I think we should take one question also from the Facebook Live people. I have copied to the chat window. I can read it for you, or you can see it, Marta. What unit did you run on this model? As I could see, that took about 5 hours, and how many samples was used to train the algorithm?
So details. I cannot answer this for you right now. Sorry for that. We have more details in our paper. I'll send pointers to this chat at the beginning of next talk. And if you get in touch with me, I'll find specific details.
Okay. Thank you, Marta. Yes, makes sense. It's not easy to follow this implementation aspect. So, thank you again for your excellent and very informative presentation. We were very glad to have you with us. It seems that we will also need another time. So, thanks again.
Yanis, it was really a pleasure to have this opportunity to meet the consortium. I honestly hope that I'll be able to meet all of you in person also and have more, fruitful discussions.
Of course.
In the meantime, don't hesitate to get in touch, any of you.
Thank you very much. So we go on with our next presentation from Dr. Yannis Mademlis. So Yannis, can you please share your slides? Very nice. So Dr. Mademlis did his studies and the PhD with the Aristotle University of Thessaloniki, and now he's a postdoc researcher in Aristotle University as well. His main interests are in machine learning and computer vision. And he has done a lot of work in UAVs as well. But today he's going to present the talk on generative adversarial networks in multimedia creation. So, Yannis, we have 20 minutes. If you can please stay on time.
Yes, I will try. Can you hear me well?
Yes, thank you very much. So you can open, you can also switch on your camera if you like, since you are presenting.
I'm afraid I don't have a working webcam right now.
Okay, no problem.
Okay, so I will present a short overview of generative adversarial networks for various media production applications. Note that this is a lecture at a more introductory level than the one by Marta, much more introductory. So, we begin with generative models, which are learning models employed for approximating the data generating distribution from which a dataset has been sampled. This can be used both for unsupervised and for supervised learning problems. Generative models in general can be contrasted against discriminative models, where supervision labels are typically necessary, where the goal of training is to learn decision boundaries in the data point space. As in most machine learning models, a generative model is defined by a set of parameters which are being optimized by training on a specific data set. After training, the parameters are typically kept fixed, since now they encode an approximation to the distribution of the data. Generative adversarial networks are generative models based on deep neural networks. After they have been trained, they capture the data distribution implicitly by facilitating sampling from the approximation, the encoded approximation. Therefore, the most important use case is in generating realistic novel data points that meaningfully resemble the ones employed during training, the so-called fakes. This can be images, videos, music, etc., depending on what kind of data set was used for training. As a result, a great deal of different computational tasks can be solved using GANs, including the tasks previously presented by Marta. So, a GAN is composed of two interacting deep neural networks, the generator and the discriminator. As you can see in the image, while the GAN is being trained, the generator generates a fake data point, for example, an image, given an input random noise vector, and the discriminator, which in the most basic formulation is a binary classifier, tries to recognize whether it is a fake coming from the generator or a real data point coming from the training dataset. Therefore, when training the discriminator, we feed it both fakes and real examples, properly labeled under a supervised classification setting. The overall idea is thus to exploit the techniques typically used in training discriminative models for constructing a generative model. Below we use WG and WD to denote the corresponding parameter sets of the generator and the discriminator. Optimal WD and WG are typically found using iterative gradient descent and backpropagation, as in typical deep learning approaches. Both the generator and the discriminator are trained independently in an alternating fashion, but the individual loss of each one at each training iteration is a function of the output of the other one. Regarding the basic neural network architecture, it depends on the kind of data that we want to generate. Most GNNs are used in GANs that manipulate images, as previously shown by Marta, while RNNs, such as LSTMs, are also commonly employed in tasks involving sequential data. During training, only the discriminator has direct access to the training dataset. And when GANs were first introduced, it was noticed that this acts as a built-in protection of the generator against easy overfitting. After training is complete, the discriminator is typically discarded, and the generator can be employed to take data points from the approximation of the empirical distribution of the training set, which has now been encoded in the model parameters. The basic formulation of GAN training can be theoretically summarized at a high level of abstraction as a minimax gain in the form of the you see in this formula. Here, D of X discriminator for input X, and G of Z is the output of the generator for input Z, where he is either a fake produced by the generator or an actual data point from the training set, while Z is a random noise vector. In essence, this optimization process attempts to maximize the ability of the discriminator to actually differentiate between real and fake data points, while concurrently maximizing the ability of the generator to fool the discriminator in this task. Thus, in the end, the generator has learned how to successfully and realistically mimic real data points from the training set. Although GANs have significantly evolved over time, especially with regard to the loss functions and training objectives, this basic formulation allows us to clearly see that the desired solution, that is the optimal WG and WD parameters, is in fact a NAS equilibrium point. From game theory, we know that reaching NAS equilibria is a very hard optimization problem, which explains the noticeable difficulty in successful and stable training GANs. Now, GANs have significantly evolved over time, and several variants have been proposed for various tasks. One of the most important such variants is the conditional GAN, also previously mentioned, GAN, which in its most basic form permits the generation of fake data points belonging to a specific desired class in multi-class datasets. This can be done both to the generator and to the discriminator an additional input during training, the condition, which, for instance, in multi-class datasets can be coded in class label. More recent variants of conditional GAN may be employed for image translation, where the objective is to learn a transform image domains, say, for instance, semantic map and RGB image, time and nighttime views. In this scenario, the available dataset consists of strict examples from two different image domains. The goal of the trained generator is to be able to realistically transform its input from domain A to domain B, with the input from domain A acting as a condition. In each training iteration, a generator input-output coupled with input belonging to domain A and drawn from the dataset, while the corresponding output is synthesized by the generator, is jointly provided to the discriminator as a single fake training example. an actual coupled image pair drawn from the dataset, where input-output belongs to the two domains respectively, is jointly provided to the discriminator as a single real example. So we have two classes, fake and real. Typically, a regression loss term, for instance, an L2 norm reconstruction loss, is added to the training objective of the generator for penalizing the deviation of its synthesized output from the corresponding domain B image known from the dataset. Thus, the generator learns the desired cross-domain mapping, as well as to realistically generalize when given novel inputs. GANs has skyrocketed over the years. As we can see here, since their initial appearance in 2014, more than 600 variants have been proposed for various tasks, most commonly involving media generation scenarios. Earliest examples of GANs relate to media are text-to-image tasks, sentence in natural language, and the set of images fitting the textual description must then be constructed by the generator. A good example is a stacked GAN, which is composed of two consecutive conditional GANs. The first one is conditioned on a representation of the input textual description, while the second one is conditioned on the low resolution output of the previous generator. Thus, the final result is the high resolution output of the second generator. This architecture facilitates the generation of realistically looking high resolution images, which was a problem to achieve realistic images at high resolutions before that. Some relevant examples of input captions, the corresponding ground truth images, for example, used for evaluation, and the generated samples. For example, a woman in a yellow tank top is doing yoga, produces these samples, these fake samples we see here, which are not that much different from the ground truth label, which is the ground truth image. The inverse task is image to text captioning, which can also be easily handled by GAN. A nice architectural example is depicted here. The image is first semantically using a CNN, possibly pre-trained on ImageNet, and this representation is fed to a sequential RNN decoder, typically an LSTM, which operates in consecutive time instances. At each time instance, the next word from the desired caption is outputted by the RNN. In order to train this specific architecture, the generator is employed as an agent under a reinforcement learning setting, and the discriminator's output is used as part of the reward signal. Of course, this is not the usual GAN training setting, but this is why I chose to show it. Here you can see a few examples of image captioning, when the input is the image in the upper row, and below you can see what captions have been generated by different algorithms. Several variants have appeared over the years for similar tasks. Here we have a video captioning GAN-based architecture. I won't go into detail for this because we're pressed for time. But here are some results. The generator produces a caption for an entire video sequence. In essence, this is a sequence-to-sequence problem where the sequence of video frames is mapped to the desired sequence of words. And since this is trained using a discriminator and an adversarial loss, it is a GAN-based architecture. A different GAN application is for synthesizing different input images taken from a different viewing angle. In this specific, which is showcased here, the goal is to synthesize the frontal facial view, given, for example, a profile image of a person's head. This can be employed for facilitating better face recognition, for instance. so that each time we obtain a view of a face from any viewing angle, we can transform it into a canonical frontal view and thus make the problem easier for the face recognizer. Here you can see a few results of face synthesis. The upper row is the synthesized image, given the corresponding image from the row below, which is the input. Now we give an example of GANs for image-to-image translation. In this specific example, the domain of photos depicting people is mapped to the domain of clothing item images. This is useful for commercial applications. It can suggest merchandise based on celebrity pictures. Here we see some input-output pairs of the trained generator taken from the publication of pixel GAN. One of the best early examples of GANs for image-to-image translation was Pix-to-Pix, which was also used by Marta, as previously said. This architecture was later improved in the HD version in order to be able to generate realistic, non-blurry, high-resolution images. This HD variant trains a CNN-based generator on lower resolution images, and then another CNN is appended to the first one, and the two networks are trained jointly on high-resolution images, using, of course, a discriminator and an adversarial loss. And in general, the potential applications of image-to-image translation are almost limitless in media. Here you can see some examples of translating daytime to nighttime views or aerial photographs into city maps. Also, these have been taken from the publication of Pix-to-Pix. I believe they were also shown previously by Martha. Here you can see some coupled triplets of input image, ground truth image, and trained generator output. In general, the generated images are highly convincing and plausible. This is a relevant example from our work in the Aristotle University of Thessaloniki, where we transform sparse geographical point of interest scatter maps into realistic-looking satellite terrain images. We see the input image, which also encodes geographical longitude, latitude, and altitude for each point of interest. Next to it, we see the ground truth, which is used for evaluation. This was not used for training. And the image predicted by the trained GAN. The goal was not to replicate of course, the ground truth image, but simply to make the network generate a realistic and plausible satellite image, given very few inputs, the data points in the input image. The geographical landmarks in the input image. A very important architecture related to image-to-image translation was cyclic GAN, an important extension to regular conditional GAN. Unlike conventional conditional GANs, cyclic GANs do not require strictly coupled cross-domain data point pairs. This is the strength. They provide examples from the two domains need not be related. For training, we just take a bunch of images from the first domain and a bunch of images from the second domain, which is a data set much easier to obtain than coupled pairs. Cyclic GAN works by using two GANs, which are trained concurrently, and adding a circular consistency loss term to the training objective. This loss term penalizes the deviation of the second generator's output from the first generator's input when the second generator is given the output of the first one as input, and vice versa. It is a clever hack to avoid the need for coupled data point pairs. Here you can see examples of painting style transfer using cycle GANs instead of using dedicated style transfer neural networks. You see some examples of season transfer in images using cycle GANs. As you can see, the produced image is highly realistic. And moving on now, a more advanced extension was StarGAN, which achieves multi-domain image-to-image translation with a single generator that is given a set of image domains. The same neural network can be used for translating among any pair of these domains. Instead of learning a fixed translation, it takes in as inputs both an image and a label. Learning to flexibly translate the image into the domain indicated by the label, for example, happy or sad. StarGAN example, where the same generator can handle many different types of domains, as indicated by the label, blonde hair, gender, age, etc. Now, image enhancement and restoration applications are also a very fitting field for GANs in the media sector. This part of the presentation overlaps with the lecture by Marta. Here we see a GAN-based architecture for imaging.
Yannis, sorry to interrupt. If you can please close in 2-3 minutes.
Yes.
So, okay.
An example of ink painting. These are the results achieved by GANs. We can see that they are much better than the results by the dedicated ink painting algorithm from Photoshop. We also have a few examples for super resolution. Also, we can see that this SRGAN output is the closest one to the original that we want to approximate. Now we have an example for image blurring. Of GANs in image manipulation, image enhancement, image restoration tasks are almost limitless. We close with different kind of example. GAN for music generation, MIDINET is a conditional GAN for automatic music synthesis. It uses a CNN as a generator. The CNN creates MIDI melodies, sequence of musical notes, one bar after another, thus synthesizing music in the symbolic domain. Representations of bars generated in previous time instances are used as the condition. The discriminator learns, of course, to differentiate between synthesized and real melodies during training. And since this is a CNN-based GAN architecture, it is very different to LSTM-based neural architecture typically used for similar tasks. So this marks the end of my short overview. I'd like to thank you all for your attention. I have also included the references to the papers if the presentation becomes available online. And that's it.
Okay, Yannis, thank you very much. This was a very nice overview of papers, approaches, applications, a very good collection of reference. I think a very useful introduction for people starting working on this field, but also for people who have already some experience in the field. I don't know if there are any questions. You can raise your hand in WebEx or comment in Facebook Live. I do not, Roberto, I guess your hand is, let's say, raised from a previous question, or you want to ask something here as well? most probably already there from before. Let me check also in Facebook. Otherwise, I have a question myself. Okay. So, Yanis, I would like to ask, of course, you saw all these very nice applications and existing work which achieve very nice results. What do you think in general are the challenges and limitations of these approaches in order to give these results?
Well, in general, the most significant challenge faced by GANs is the mode collapse problem. I don't think it's the mode collapse problem where the generator produces only a few different images or fake data points and cannot achieve diversity in results. This is a typical problem when training GANs. So I believe this can only be solved by methodological advances. We have not yet achieved the point in GAN research that this can consider. So that's the most important challenge.
Okay. Thank you very much. There is one request to move to the previous slide. People want to see the list of the beginning. Okay, or this list, the first slide of references. Okay, okay. So, Yanis, thank you very much. I guess your presentation and the other presentations will become available in the workshop website, and this will be disseminated by our Twitter and main site accounts. So, thank you very much. So I have the pleasure now to introduce Dr. Vasilis Mezaris, a senior researcher. We are here together in CERTHEP ITI. Vasilis did his studies. Vasilis, if you like, you can start sharing your slides.
Yes.
And Vasilis, thank you very much. Did his studies with Aristotle University of Thessaloniki, obtaining his PhD from this university. Then he started. Then he joined CERT ITI. Currently, he is a senior researcher, a research director in CERT ITI. And his interests are in general with visual content analysis, and especially with video summarization and shot detection related approaches. So the talk today will be GAN-based video summarization. So, Vasilis, if we can fit the presentation within, let's say, 15 minutes, so we also have some time for questions. Thank you very much.
Sure. Thank you, Yanis, for the introduction. Can you see my slides? Can you see my slides?
Yes, we can see, also see you and hear you very well.
Okay, great. Thank you, Yanis, then for the introduction. This is joint work with colleagues in my group, Vlampios Apostolidis, Elena Damandidou, and Alexandros Metsai, and also Yannis Patras from Queen Mary University of London. So, starting with GAN-based video summarization, what is the problem? We want to generate a video summary. So, starting from an original video, we want to select different bits and pieces of the video and present them either as a set of keyframes, which is a storyboard, or as a shorter video that can be viewed instead of the original one. And why do we want to do this? There are many applications. These include being able to preview content in content management systems, being able to repurpose content and share it across different social media platforms, generating movie trailers, and in more specific domains, also things like generating sports highlights videos from the full-length game videos, or generating a video synopsis of surveillance recordings. So there are many applications of video summarization. In recent years, video summarization is addressed by using deep learning approaches. And there are two main categories of approaches here, supervised deep learning methods and unsupervised ones. So the supervised methods, they use ground truth summaries, ground truth manually generated summaries of the videos together with the original videos to train a deep network to generate a summary. And here we have a multitude of approaches, some using feed-forward neural networks, or CNNs, others looking at not just the visual content, but also exploiting metadata about the video, using LSTMs to capture the flow of the story, and many, many other approaches. On the other side, there are unsupervised algorithms that try to learn how to build summaries without having access to ground truth manually generated summaries. So looking at just sets of videos to train. And here is where we have primarily the use of GANs. So there are many approaches that use adversarial learning for this application. I will not say more about the state of the art, the literature in video summarization and GANs, because this is quite extensive. But I can point you to a tutorial at ICME 2020 that we presented a few months ago, where we discuss in detail the literature and the different works in this domain. What I want to take as a take-home message from this slide is that there are certain advantages of unsupervised algorithms, so GAN-based algorithms, which is, of course, that there is no need for using training data, which is hard to produce, and even when we have them, they are quite limited in volume. We can avoid the subjectivity and biases of using this kind of manually generated ground truth summaries, because understandably, if any one of us is given a video and is asked to produce a summary, we will most likely produce all sorts of different variations of summaries. There won't be a unique summary video that we can all converge to. And then, of course, since we don't need this kind of training data, it is easy to train the algorithm and retrain it on different types of video again and again to adapt to this kind of different types of videos that we want to be summarized. So our starting point for this talk and for our work is the SumGAN architecture, which is shown on this slide. The main idea is that we want to build a keyframe selection mechanism that selects keyframes and ultimately video fragments and minimizes the distance between this set of video fragments, this summary, and the original video. So it tries to make the video summary as indistinguishable as possible from the original video. And then the problem is how to define a good distance, how to quantify this. And the solution here is to use a trainable discriminator network. So we have a summarizer that tries to confuse a discriminator, which again is trained to discriminate between summaries and original videos. So this is an architecture that is trained all together. So together we train the frame selector that generates the summaries, the encoder decoder, and the discriminator that tries to discriminate, tries to say if the summary, if the video that comes as input to it is a summary or if it's the original video. So then on top of this SumGAN architecture, we did some studies and we produced some extensions. And I would like to present, to start with the SumGAN SL architecture, which is a variation of the previous one that introduces two extensions. One is a linear compression layer, which we can see on the right-hand side of the slide in the yellow rectangle. And the other is an incremental approach to training the components of the model. So the introduction of the linear compression is quite clear, I think. This is a fully connected layer that reduces the dimensionality of the input vectors. So the video goes through a CNN, there's certain features extracted for the frames of the video, and then with the linear compression layer, we reduce the dimensionality of these feature vectors. This helps a lot with then training the rest of the network. As concerns the training, the incremental approach to training, So typically, one would update the weights of all the components in one step. Instead of doing this, we broke down each update step to 3 sub-steps, and this is what is shown here on this slide. So in the first sub-step of updating the weights, every time we need to update the weights of the network, we start with the first 3 components here. So linear compression layer, frame selector, and the encoder. Then in a second step, we go on to update the decoder and generator, and again, the linear compression layer weights. And in a third step, we update the weights of the discriminator and again, the linear compression layer. So this kind of incremental approach was shown to help a lot in training the network and getting good results. And I think the take-home message here is that sometimes it's not the great changes or the major changes in the architecture of a network that make a big difference, but also nasty little details like how exactly you do the update of the weights, or as we saw in Marta's presentation earlier, how you do the normalization, how you combine instance and batch normalization in that case. A second extension that we created on top of the previous one is the SumGAN AAE architecture. So this is where we changed the variational autoencoder of the previous architecture with a new attention autoencoder. So we introduced this attention layer that is shown on the diagram. So how does this work? This is the attention autoencoder. So we have the weighted features, the encoder's output, and then we have these attention weights here that are calculated and then are used to update the encoder's output, so that we have these new V vectors that are used then in the decoder. So this is what the attention layer does here. And this is where I try to briefly explain how we train these architectures and how we develop them. So in practice, after we have trained these architectures, how do we do the summarization? We get the original video, we have it go through a CNN, so we extract the features for the frames. And then we have these features go through the linear compression layer and the frame selector. So then the frame selector gives us the important scores that it has been trained to generate. Then we get a segmentation of the video into temporal fragments, and based on these frame level importance scores coming out of the frame selector, we calculate fragment level importance scores, and then given a time budget for the summary, so how long we want the summary to be, we solve an AppSec problem to select the most important fragments to fill this time budget. A few words on datasets and evaluation. So the two most popular datasets in this domain is SAMI and TVSUM. They're made of a few videos each, and they come with ground truth summaries. And the general idea of the evaluation protocol is to try to quantify for whatever summary we generate by our method, how much it overlaps with the ground truth summaries. And then because we have multiple summaries per video generated by different users, there are different variations of the protocol that look, for instance, at how the generated summary compares with every one of these summaries, the ground truth summaries, and then there are different dataset specific ways according to the original works that presented these datasets on how to calculate the measure, the evaluation measure, the F-score in every one of these datasets. And there's alternative evaluation protocols. So the evaluation in this problem is not straightforward, and there are quite a few variations in the literature, but we don't have to worry about this at this stage. So some implementation details here about the networks and the experiments that we did. So videos were downsampled to 2 frames per second, and you can see on the slide the details for the different layers of the architecture. And some results. First, comparing our unsupervised video summarization approaches, so SumGAN SL and SumGAN AAE, with the literature works on video summarization. We can see here that we do quite well. So this is one important take-home message, that these GAN-based architectures can work pretty well for video summary generation. Also, if we compared with the original SumGAN, which we cannot do in this slide, and I'm not showing a slide on this for the sake of brevity, but if we because the original SumGAN uses a variation of the evaluation protocol, but if we saw the results there, we could also see that there is a lot of difference between the original SumGAN and SumGAN SL. So this is what I mentioned earlier, that this fine-grained approach to updating the weights of the architecture, so not updating all the weights in one step, gave us a lot of improvement. Then a few curves showing how the convergence of the network comes. And in the horizontal axis, we see the epochs. And we can see that the introduction of the attention autoencoder in the network helped a lot with a more stable training. So this is quite important also, the qualitative features of the training of the architecture. And here we can see some comparison of, again, our GAN-based unsupervised video summarization method with several supervised summarization methods. And here, the unsupervised method that we propose is not the best overall, but it is quite interesting to see that it is one of the best, and it actually can produce comparable results to the state-of-the-art supervised summarization method. So the take-home message here is that in some problems like this, even an unsupervised method can perform pretty well and compare with supervised approaches. I have here a summarization example with an original video and a summary, but I think both for the sake of brevity and for not breaking the video stream, I will not show them. I would also like to very briefly highlight also an application of video summarization. So we use this algorithm in a variation of it to automatically generate videos, different variations, different summaries of a video that can be shared in different social media channels. So in Facebook, in Twitter, there are limitations to the videos that can be shared by these platforms. So this requires when you have an original full-length video, to summarize it in different ways in order to be able to use a summary of that content in these social media channels. And here we have built a web application for this, where you can easily upload your video or post a link to a video, select your target platform, so Facebook, Twitter, and other platforms, and you can generate a summary that respects the limitations for video for these platforms. And you can also see a demo video on how to use it, but it's fairly straightforward to use it. So to conclude, because I'm running a bit over time, we saw how GANs can be used for video summarization, and we saw that GANs are a very competitive approach for the video summarization problem. We saw how the attention autoencoder helped a lot with the performance, but also that other details in the architecture can help a lot with the performance. And finally, I would like to state that while we all strive to devise automated approaches for solving different problems, and this is what we also did for the video summarization, in many cases in the applications, complete automation is not desired. So the symbiosis of AI and the human user is the key. And this is what we see also in the video summarization problem, that in some cases, in our PreTV project that supported this work, it is desirable to generate automatically summary, but in fact not render the video summary, instead just generate the summary script and allow a user, then an editor of the video, to semi-automatically adjust some parameters of the summary before generating the final summary. So introduce somehow the human in the loop in the summarization process. So with this, I conclude, and thank you for your attention.
Thank you very much, Vasilis. Very nice presentation, very interesting applications, nice results. Thank you very much. Let me see if we have time maybe for 1-2 questions. I don't know if there are any questions. You can either raise your hands in the participant list, or you can just open your microphone and make the questions, as we do not have so many. Let me also check in Facebook. One moment. Okay, also no questions in Facebook. Let me ask you, Vasilis, how much this approach and your approach and in general this approach depend on the availability and quality of data sets, and how easily it is to obtain these data sets? So can you please elaborate a little bit more on this?
Yes, sure. So one important strength of these techniques is that we don't need ground truth annotated data sets for this, so we don't need any manual summaries. For training them, we just need a bunch of videos, and this is helpful because just raw videos we can get from anywhere. Also, if we want to adapt to a different type of video content, so go from summarizing shorter internet clips to summarizing episodes of a sitcom, then we can again retrain easily to this with this type of new content and have a summarizer suitable for this domain. Where we have an issue with the availability of datasets is when we try to objectively evaluate these approaches. So this is where we need ground truth data, of course, for quantifying, for calculating these F-scores. And in this case, there are limitations with the existing datasets. Serious limitations, both because of the size of the datasets. As you saw, SAMI and TV-SAM comprise 25 and 50 videos, respectively, which is not much. And there are also issues with the evaluation protocol and how reliable this is when you try to compare different methods and you do the evaluation using slightly different parameters, like using different splits of the dataset for doing the evaluation. And we have a paper on exactly this kind of limitations and how to overcome them at ACM Multimedia this year, so to be presented later in the month.
Regarding specific the evaluation part?
The evaluation protocols and limitations and how we can mitigate some of these limitations.
Okay, thank you very much. I don't see any other questions, so it is time to have our break. Unfortunately, in order to save some time, it has to be a shorter break than planned. So I suggest we start again at 12 minutes. This is 20 past 12 in Central European time. I will also share a slide here. So a break for 10 minutes, and we will be back with a presentation from Dr. Simon Papadopoulos on deepfake detection, one really important problem in our times. Thank you very much.
Yanis, I guess you forgot me. I think I'm before Akis.
Oh, you are before.
Yes, so this is what I see in the agenda. It doesn't matter.
Okay, Nico.
Nico, that was the original
No, I can do it.
agenda, and then
Doesn't matter to me.
you requested to switch, if you remember.
Okay, could be. Okay, fine.
I will send you the link in the chat of the website. It has been like this for some time now, okay?
Okay, fine. I can do it afterwards. Fine.
Okay, very nice, thank you.
No problem.
Hi, Yannis. I'm Luisa. I'm the last one. Just wanted to check the audio, if it was okay.
Yes, I can hear you very well. I don't know if you want to also...
Yes, share the video. Yes.
The video as well.
Perfect. That's perfect.
Okay.
Okay.
Thank you very much. Thank you. Hi again. Akis, do you want to share your slides?
Sure.
Okay, I will stop sharing.
Can you see them?
Yes, not in presentation mode, now in presentation mode as well. Very nice. Oh,
I just want to also open the camera,
okay.
so I will
Yes.
stop for a bit.
The camera looks well. Slides as well.
Okay,
Okay, so you are ready. Let's wait for a couple of minutes.
sure.
Nice. In any case, there is a delay with Facebook Live, so the slide now appeared completely in Facebook Live. We have to take also this into account. So in total, in average, around 150 persons have been watching this, following this workshop. Around 100 here in WebEx, and more or less, not right now, but before there were something like close to 50 participants in Facebook Live. So we are back. We can start with the second session of today's workshop. Three scientific research related, not three, four scientific research related presentations. Three from AI4Media members, and one from our second invited speaker, Luisa. And it is a pleasure to introduce Dr. Simeon or Akis Papadopoulos, a senior researcher in CERT ITI. Akis did his studies, graduate studies here in Aristotle University of Thessaloniki. He did his master degree in Netherlands. Then his PhD again here with Aristotle University of Thessaloniki. Then now he's, as I mentioned, a senior researcher after being a postdoc researcher. Now he's a senior researcher in CERT ITI, leading the team, the group who's working on media verification activities. And his main interests are around data mining, multimedia, and especially in media verification. And today the title of the presentation is on deepfake detection, the importance of training data pre-processing, and practical considerations. So, Akis, please.
Thank you very much for the introduction. I'm going to try to briefly present our lessons learned and the experience we gained on the problem of deepfake detection. The work to be presented here is largely motivated by our involvement in the Horizon 2020 project We Verify, where we aim at delivering a practical solution to the problem. Therefore, the talk is mostly oriented on practical matters that came up as a result of our effort in delivering a service that is usable in a realistic scenario. It's work done primarily by my colleague Chronis Charitidis, and also George Kordopatis-Zylus contributed to this work. Before proceeding further, allow me to repeat some basic background knowledge, which many of you likely already know. The term deepfakes originally appeared in 2017, so it's almost 3 years old, when a Reddit user with the name Deepfakes started posting generated videos on a specific subreddit channel. These videos, it's needless to say that they were of pornographic nature. Since then, deepfakes have gained a wide popularity and have been used for a variety of purposes, including entertainment, but also for malicious purposes like spreading disinformation and even committing financial fraud. The most common form of deepfakes involves the manipulation of human faces. And in terms of technology, they originally were based on autoencoders, but since then many extensions have been presented, typically based on generative adversarial networks. A recent survey on the topic by Tolosana and colleagues defines 4 main types of face manipulation: entire face synthesis, attribute manipulation, identity swap, or also known as face swap, and expression swap. This is, of course, a very crude view of the problem. In addition to this survey, there are 2 more very nice and comprehensive surveys on the topic. One by Professor Fertoliva, who we are very happy to have in the workshop later today, and another by Mirsky and Lee. Obviously, the fact that there are 3 surveys on this in this area coming out just this year is a clear indication of the importance that the subject has for the research community. As I told, we are doing much of this work in the context of the Horizon 2020 We Verify project. We Verify started almost a couple of years ago with the goal of developing tools that help expose misleading content and help citizens, journalists tackle disinformation on social media. Project partners include the University of Sheffield, Ontotext, ATC, Deutsche Welle, Agence Presse France, EU Disinfolab, and our team at CERT ITI. A key outcome of the project is a platform for collaborative content verification, tracking, and debunking. And as part of this platform, we have been developing a deepfake detection service. Coincidentally, at the outset of our activity, the Deepfake Detection Challenge was announced, so we decided to participate in order to delve deeper into the problem. The goal of the Deepfake Detection Challenge, which was launched last December on the Kaggle platform, was to seek the best solutions for detecting videos that contain facial and voice manipulations. The challenge was organized by a consortium of companies, namely Amazon Web Services, Facebook, Microsoft, and also the Media Integrity Steering Committee of the Partnership on AI, plus several academics. Until the submission deadline last April, more than 2,000 teams registered and participated in it. Challenge participants needed to submit their code into a black box environment for testing, and then the results were presented in a public leaderboard. Participants could submit several times their solutions, and each time they could see what was the performance in terms of log loss error against the so-called public test set. This set was called public, but in fact it was not available to participants, but the performance on this set was public. So after this period where participants could test on this public dataset, There was the submission deadline, and the participant needed to select their two best solutions according to their gut feeling to be used for the final ranking. Then these solutions were applied in this black box environment in a private dataset, and then a private leaderboard was created and was used for the final ranking and to select the winners. Among the 2,114 competing teams that successfully submitted, ours was ranked 49th in the public leaderboard. So this was among the top 2% of the solutions, and 115th in the private leaderboard, so among the top 5% of the solutions. A key starting point for developing our solution was the dataset released by the organizers of the challenge. This consisted of more than 119,000 10-second video clips, so almost 120,000 clips. And of those, 100,000 contained deepfakes, which were based on some well-known deepfake generation models. These were the deepfake autoencoder, perhaps the most well-known, the morphable mask model, also called MMNN face swap, the neural talking head model, model that is based on few examples, the FS GAN method, and a method based on style GAN. So this variety of model was considered by the organizers as representative of the state-of-the-art deepfake generation technologies at the time of the challenge. In addition, the hidden test set, which participants never had access to, included more types of false content, both resulting from data augmentation, but also sourced from actual internet sources. There is a very nice overview paper that was recently published by the organizers. I put the reference here, which offers really many interesting details. Moving on to the actual solution we devised, we should first say that a key component in the process is face extraction step, where we use one of the existing face detection libraries. And then the model training essentially happens around the face. Given that all face extraction libraries are bound to generate a number of false positives, one may understand that this can be a source of noise during the training process. And this is exactly what we aim to tackle in our work. Here is a sample of faces extracted from a few clips randomly selected from the training set at 1 frame per second. In this particular case, we used the MTCNN face detection library. One can note that there is a small noticeable portion of false detections, but overall the true detections per video are considerably more. But our aim was to eliminate even those few false detections in order to gain in terms of model accuracy. And how did we do that? We devised a filtering approach. Our goal was to cluster the extracted faces around same face clusters in order to then be able to drop the small clusters that we consider as noise. To this end, we first compute face embeddings for each detected face in the video, and then we build a face similarity graph. This was done by computing all pairwise face similarities among the respective embeddings and maintaining only edges that connect face embeddings of sufficiently high similarity. This similarity, essentially, it was a threshold that was empirically selected, but the approach was not very sensitive to this. We found that the resulting graph was then naturally organized into connected components, with large connected components corresponding to the main faces depicted in the video clips, while the small components often correspond to false face detection. And this was used to filter out the small components using a heuristic rule. As you may have noted, this is a pretty straightforward and simple approach, which means that it is very easy to apply on top of any other deepfake detection training process. Additionally, there is no need to manually tune the face extraction library in order to reduce the number of false positives, since this is what actually this preprocessing method does. Finally, a positive side effect of the method is that it naturally organizes the detected face instances in a video clip around face identities, which is useful when multiple persons are shown in a video and the analysis process needs to treat each person separately. To investigate the effectiveness of this approach, we used it in combination with different models and on different test datasets. Specifically, we trained multiple deepfake detection models on the training set of the challenge, and with and without the proposed preprocessing step. And we tested then on 3 established benchmark datasets, CELEB-TF, Face Forensics ++, and an independent subset of the deepfake detection challenge. We also experimented with different ways of aggregating different frame predictions from frame level into video level prediction. In this slide, I just present the results of the EfficientNet B4 model using 2 aggregation methods, but we've also done experiments using the well-known MesoInception 4 and the ExceptionNet model, as well as 2 additional aggregation schemes. In all cases, we notice that the proposed preprocessing step leads to a measurable reduction in the deepfake detection error in the order of about 5%. So this means that with this very simple addition of this step, it's easy to gain a modest but still significant accuracy for the model. Of course, this preprocessing step is just a small part of the whole training pipeline and solution. And there are really many different details and practical aspects that need care in order to end up with a high-performing system. In addition to the proposed filtering approach, we observed that detection performance and robustness benefited a lot from face augmentation step. This involved generating more samples based on different transformations, including horizontal and vertical flip, random cropping, rotation, image compression, Gaussian and motion blurring, brightness, saturation, and contrast transformations. We also used an ensemble of 3 models, EfficientNet P3, P4, and I3D, without the optical flow, averaging their predictions. On each of those models, we added 2 dense layers with dropout after the backbone architecture. Other details include the oversampling of frames from real videos to compensate for their smaller number in the training set, random shuffling across all extracted faces to create training patches, and the use of an ADAM optimizer with a learning rate of 10 to the power of -4. At inference time, we again first apply the proposed preprocessing step, and then we obtain the components that correspond to the different faces in the video. We then extract 48 uniformly sampled frames from the video and use the trained models to get predictions per detected face. We average model predictions for each face component and model. In case of multiple faces, we then output the maximum prediction among the aggregated face prediction as the final prediction for the video. After the challenge, we had the opportunity to study the details of some of the best performing methods, and we took some valuable lessons. First, most approaches seem to use ensembles of architectures, in particular the EfficientNet architecture and all its instances, so B3 to B7. RES next was another architecture that was used by top performing solutions, combined with 3D architectures such as I3D, 3D ResNet, 3.4, MC3, etc. A very simple heuristic that seemed to work for some participants was to increase the margin around the detected bounding folks around the face. In our solution, we used a 20% additional margin, but it seemed that even larger values would lead to further gains. And also to improve generalization performance, some additional domain-specific augmentations proved to be beneficial for some teams, like half-face removal, be that horizontal or vertical, landmark removal, by landmark I mean nose, eyes, and so on. And even some solution tried mix-up augmentations, which led to further increases. Trying to summarize the practical challenges we faced, the most important one seems to be the limited generalization ability of our model. This, of course, this observation doesn't only apply to our case, but to all participants of the challenge, since, for instance, the winning team scored 0.2336 log loss error in the public validation, but then only 0.4279 error in the private one. So we see a considerable increase of the error in the unknown set. Overfitting seemed to also be a big issue for some participants. A noteworthy example is that the top method in the public leaderboard, which had scored 0.19 in terms of log loss error, then was really dropped significantly in the private leaderboard to only 0.57 error, and that was below the 900th position. Finally, a related cause for these challenges, we think, is the problem that the deepfake detection has a very broad scope as a problem. It includes really many different types of manipulations and generative models, and given its adversarial nature, we are almost certain to have access to only a subset of the types of manipulation at training time. Also, I would like to list a few challenges that we are currently facing in our effort to deploy the service in the wild. First of all, video sourced from the internet may contain multiple scenes and shots, and only a subset of those may contain a deepfake. Processing and aggregating the results per scene can significantly slow down our service and also make it much harder to present the results in an easy way to end users. Also, it seems that the bulk of social media videos are of low quality, and low quality faces tend to fool classifiers, at least the models that we have built so far. Other challenging cases include small and fast moving faces, while changes in illumination and moving objects in front of faces pose additional problems to the model. Therefore, robustly handling the variety of internet content seems to be a really big task we have ahead of us. As said before, this work is done within WeVerify, and we have recently released to the project partners a deepfake detection service that is currently undergoing testing with our media partners, Agence France Presse and Deutsche Welle. It is still not publicly available, but if some of you are interested, please drop me an email and we could grant you test access. For people interested in the more technical details, a paper is already available on archive and will be presented in the Conference for Truth and Trust Online later this month. And with that, I would like to thank you for your attention and give you the contact information in case you have any questions, or of course, I'm happy to take them here.
Thank you very much, Akis. Really interesting presentation and useful, I think, highlighting also the practical, some practical aspects and some very useful lessons learned in this topic. I don't know if there are questions. You can either raise your hand in the participant list or just switch on your microphone and ask. In Facebook Live, you can comment. Let me check if there's anything in Facebook Live. Okay. Akis, I would like to ask something regarding this interesting results on generalization and these limitations that you show. Since maybe the distinction between this public and private way of evaluating the algorithm is not so clear. Can you please clarify what was the different setup between this public and private evaluation, which
yes. During the challenge, while the challenge was open, the participants had the chance to submit their code, essentially the models they had built, to this black box environment of the Kaggle platform. And then the models were executed, and after some time, the results appeared on the leaderboard. So a participant had the chance to see whether the change that they did in their model had a positive or negative impact on the results. And this was essentially used by some teams to kind of overfit to this public test set, even without having access to the test set. So they tried out many different things. Of course, there was this private test set that was never accessible in any way by the teams, and this was only used for the final ranking of participants. And so this also, as was revealed in the paper by the organizers, contained additional examples that were not contained in the training and public test set. And that's why most teams didn't manage to have an effective safe solution for the private
I guess just a small comment from me. I'm Luisa, and probably it seems that they also considered YouTube videos, and
yes.
Of course they have a very different pipeline in terms of compression with respect to the training data they gave. So beyond the different type of manipulation, maybe this was also a problem.
Yes.
Yeah, I think there were almost half of the data set.
That's true. Yes. Thank you very much for this clarification.
Okay, thank you very much. Very interesting evaluation approach in order to highlight also limitations of the approaches. Thank you very much, Akis. And now we go on with our next speaker, Professor Nikos Sebe from University of Trento. If I start presenting in detail the positions and the achievements of Nico, we will need a time slot equal to a presentation. So I will just stay with his current positions, being the head of department in the Information Engineering and Computer Science Department at the University of Trento, leading there the multimedia and human understanding group. And Nico has a very impressive list of achievements regarding publications, events organization, best paper awards, and so on. He is a well-known expert in multimedia and the computer vision area. And his talk today will be on image and video generation, a deep learning approach. Nico, thank you very much for participating in the workshop and looking forward to the talk. You are muted.
Okay, I hope now should be fine, I guess.
Yes.
Wonderful. So thanks a lot for the kind words. Of course, all the work is done by my students. So I'm the one, let's say, creating noise most of it and presenting their results. So just to make it clear from the beginning that we are on the wrong side, in the sense that we are the bad guys trying to generate images and videos, and this could also be regarded as fakes. I will give you some examples, and will tell you why do we want to do all these kind of things. Okay, let's try to see if this works. Good. Let me start with a teaser. So practically, this is a video. You can probably tell it's a fake video because there are a little bit of deformations, also in the background, but also on my face. And practically, this was just simply generated from my image on the web page, and so it's really a static image. And then it is, as you see, the video is driven by a moving face. by some guy, some random guy, and that was created by one of my students. It's a little bit out of sync. Well, this is because of the PowerPoint, but they are perfectly synchronized, and I will show you some examples later. Okay, so what I will discuss today would be, let's say, 3 topics. So one would be using deep generative models for. So we will start from generating videos of facial expressions, but belonging to the same class, let's say like a smile, but we want to have variety into this video. So you want to generate different types of smiles, like posed, like spontaneous, like tense, and so on. Another topic that I will discuss is image generation. So practically you just have a target image and a target pose, and a source image and a target pose. And what you would want to do is to generate the image into the target pose. And finally, I will talk about arbitrary object animation without 3D modeling. So practically what you said before, you have a static image, you have a driving video, and then you want to generate a video that practically copies the motion of the driving video without having any constraints, without having any 3D modeling of the object. Okay, so the first topic. So these are 2 things done by my student, mostly by student Wei Wang, and it was a CVPR paper, and now it is a transactional multimedia paper in just in press. So this is practically what we want to do, is to do a landmark guided diverse smile generation. So starting with a conditioning label, right? So you want to have like posed, creepy, nervous, spontaneous, overreacting smile. You have a neutral face, and you want to use a conditional adversarial recurrent network to generate a video, right? So you generate videos from the smile class, but having these labels. Right, so you start generating sequences of smiles conditioned on the labels. You generate k different sequences of smiles, and you also want to make sure that you are keeping the identity of the person. Right, so the challenge is that you need to have. So this is conditioned on priors. Right, you are doing one to many. So practically, you start with from a single face, but you are generating multiple videos, and you want to preserve the identity. Right, so you have a landmark sequence, and you want to say you are keeping the real face identity via the unit. I'm not going to provide you many details, but so you can get them in the paper. But I will tell you exactly how it works. So practically, you have different modules in here. You have a facial expression. So as an input, you have neutral face, landmarks, and conditional label. So you are extracting landmark on the face. Then we are generating sequences of landmarks. So we are not generating, let's say, pixels in this case. But then at the end, practically, we are doing a landmark sequence to video translation, right? So practically, we are generating the formation of the landmarks. And the reason for this is that this is much cheaper than just generating different pixels. And then we do a sort of in-painting on top of the landmark that we have using the neutral face that we had at the beginning. Yeah, so you started in the left with encoding the landmark image and generate a sequence of landmarks embeddings according to the conditioning labels. Then we generate k different landmark embedding sequences. So here the idea is to have these sequences as far away as possible from each other, but still making sure that they belong to the same class, so in this case, smiles. And then in the end, we translate each of the sequences into a face video. So let me show you a demo here. So we have a face going from neutral to smile to neutral back again. So what you can see here is that you have different differences into spontaneous and post smiles. So the intensity of the face, the intensity of the smile is different, and so on. So here is another example with another face. So you can see a wide open mouth while the other one are closed, and so on. Okay, so here practically we have the variation. So this is the variety that we are imposing on the deformation of the landmarks. And here you can see examples with the state of the art. So ours is the one highlighted. So what you can tell, let me try to stop it somewhere. Our has less artifacts. So if you look at video GANs, it looks pretty bad. And also, if you look at the cronets, it's also losing a lot of the identity. So here you have a lot of distortion from the identity point of view. While ours, it's quite reasonable from this point of view. Okay. So why is this useful? Well, it's quite useful for, and this is what we also show in the paper. It's useful for doing better training. So, for example, in some classes, you don't have enough training data, for example, for post smiles. And doing this type of video generation, it's helping you in doing data augmentation for training. And that's that we show that it's working pretty well in this case. So if you are using these solid and fake videos, if you want, it will help you learn a better classifier when you want to classify, for example, fake smiles or spontaneous smiles. The second topic that I want to discuss very briefly, it's pose-based human image generation. So this is a work done by my students, Alex, and my former postdoc, Stefan, and my postdoc, Enver. So, and this is a paper, we had a paper at CVPR 18, and now it's a paper in PAMI, just in press. So very simple here. So practically, as I mentioned at the beginning, we have a source image. We have a generation, and we want to predict how the appearance of this particular person into a target pose, right? And then practically we are using ground truths to discriminate. So we have a discriminator to discriminate between real or fake. If what we get in there is real or fake, and then we do the looping. So why this is different from generic image generation? Well, if you are using a rigid scene generation task, there the local structures are always well aligned. While in this case, we don't have this special alignment between the input and the output. Okay, and this is seen if you, for example, you put an image and you want to generate the new target. If you just do it through a neural network, you would see that practically the region in the source image would correspond to a different region into the target image. And this means that we need a deformation model. So what we did practically for each specific body part, you see here in the P of XA, we compute an affine transformation. And then we use this function, we are learning this function FH to move the corresponding feature map content. Okay, so practically you just get the segments that you get in there, and you move them into the right position into the target pose. Okay, so what you have into the stream target, to the target stream, you have the target pose. We are using a heat map using Gaussian blurring, so just to allow for noise into the key points estimation and the segment estimation of the body. Then we have feature maps that are shuttled by skip connection from the HB, so from the heat map target. And then we are obtaining feature maps directly obtained using the up convolutional filters applied to the previous layer markers. And then we have the joint locations in XA and AJ. So these are specially aligned by construction because it's a target extracted from the source stream. Then in the HB, the joint location may be far apart from the XA. And then from there, we don't concatenate HB with the other input tensors. So practically, we are just putting it directly into the target stream. So again, I'm not providing too many details. If you are interested, you can look into the paper. But here are some results. So this is on market data set. You see this is the source image. This is the target pose. And these are the generated images. This is the ground truth. And these are the generated images for our method. You see it's working pretty well. It's also able to generate reasonable well also when you have, let's say, objects like, the backpack and so on. It's also keeping reasonable well the texture of the original image. And it's also able to work very well with changes in scales. So this is here are some examples. So you can you can see also the texture is generated. And also, in many of the cases, for example, in the baseline, you are losing computing the texture of the image. So like in the second row. Some examples in which our method didn't really work, and this had to do with some errors of the pose estimation. Sometimes you have ambiguity in the pose estimation. So, for example, when you get the target pose, you don't know if the person is from the front or from the back. So this may have some troubles. We may have troubles with some rare object appearances. So, for example, on the last row, you have the purse, and this is not reconstructed well into our example, right? Because we don't have enough examples to see, for example, this type of occlusions, or in the case of very, very rare poses. So there we may have some small problems. Okay, finally, I will discuss the image animation. So this it's some recent work, and now we are improving it. Has been used quite a lot for creating fake videos, and practically you can check yourself the code that is available at the link that I'm indicating in the slide, and to create your own video animation yourself. So practically here, what we want to do is not to do we don't want to do only appearance transfer, but also to do motion transfer, right? So if you do only appearance transfer, then it detects the pose in each frame of the driving video, and apply our pose-based image generator that I presented before with a sort image and each detected pose, right? The problem is that it requires a detector and does not work when the shape of the object is different, right? If you can have a short to tall person, or for example, you have it here, you have like, I don't know, it's a dog and you want to transfer the motion to a horse. Okay, so there are two different objects, but still the motion is the same. So practically what we propose here is to use unsupervised motion transfer. So very simple, you start with a particular video. You just extract key points. You have the target video, the target image that you have in the beginning, but you observe that you have some displacement into the stuff, right? So again, here we have an alignment problem. So what we do for the monkey net, we have a specific key point detector, delta, a motion prediction, M, and an image generator, right, which reconstructs the image from the key point position and in the delta. And then we are reconstructing the optical flow from computed by M in order to be used by G to handle misalignments. Okay, so this is the motion prediction. So from the appearance of the first frame and the key point motion, the network M predicts a mask of each key point and the residual motion. And then at the testing time, the model generates a video with the object appearance of the source image, but with a motion from the driving video. Okay. Let me go to some examples. This is low resolution, but I'm going to show you some higher resolution images. So practically, you have a static image, you have a driving video, and you are animating that image. You see also that the background is preserved, and you are animating these images to do, let's say, the Tai Chi movement that the guy in the driving video is doing. So please, sometimes, especially in the background, you have some artifacts, but it's pretty reasonable also in changing in the scale. A second example, it's also to show that it's working on animated characters. You have a driving dog, which is moving, but you have a lot of animals, like, I don't know, a horse or other kind of things, and they are still able you are still able to generate the motion. So practically here we have no constraints. The only thing that it makes sense is that you need to have some kind of coherent motion, right? So you cannot just drive an image of a person to run like a dog, okay? Because the motions are not compatible. Of course, an easy way of doing it is just using faces, and this is just an example, right? So you have the two driving videos, popular ones, given the American elections. You get a few examples here of static images, and they are driven by the moving video. Okay, so you can see the result is quite good, I would say. Probably it will not be, let's say, it will easily be detected by a fake video generator, but As I said, here we are imposing no constraints at all. So the algorithm is completely agnostic of the fact that this is a face or could be any object, as long as we are able to match the key points. And as the last stuff I want to show you, so this is a video which I took from the internet. There is one guy that is doing practically, he's commenting technologies, going around and he's finding technology and he's creating his own 2 minutes video presentations, and he is trying the technology. So what he did, he downloaded our code, and then he created his own fake videos. And this is the example of what we sent. I don't know if you can hear the sound. Can you hear the sound of the video?
Yes, yes.
Okay.
No, not yet. No, sorry, no. Hello, good morning. Now, yes, it's the best.
Okay, okay. So practically what he did here, is created his own video, and he's testing our technology. I'm not going to play all the video, but let me go towards the end. Okay, so once again, we had nothing to do with this video. So the guy took our code and then he created this, let's say, comment synthesis video using our code. So you can also take it, you can also play with it, and I think it's quite reasonable to see. This is use well, some motion characters, but you can put anything you want in it. Okay, so this is all I wanted to talk, and of course I'm open for answers.
Thank you very much, Nico. Really interesting presentation and results. I don't know if there are questions. Yes, there are questions. Akis, please go ahead.
Hi, Nico. Really exciting topic and talk. I was really surprised that this guy managed to create such high quality results. Do you know whether this is a guy with a really in-depth background in the area, or is he just a tech-savvy guy?
No, he doesn't have the background in the areas. He practically is digging for technology and he's presenting it around. So I guess he may have some computer vision computer science background, but it has nothing to do with this topic. So he's creating this type of videos for different topics. So I imagine that so practically everybody with a little bit of let's say knowledge on coding can take our code and just play it and create videos.
And then another practical question, is it very resource hungry? Would one need a very expensive equipment, or can it be done on off-the-shelf GPU?
Off-the-shelf GPUs will work for sure.
Okay. Thank you.
Yeah.
Okay, thank you very much. We have another question from Amin Honarmadi, please.
Hello, thank you so much for a nice presentation. My question is, what is your evaluation? Is it for your model? How is it good? How we can consider your model performance is good, like objective evaluation or subjective? And another question is, did you consider the pose as a condition for your model? How did you produce some video with the same pose? Thank you.
Of course, I didn't, especially for the video animation, of course, I didn't show you these numbers. I was skipping through the slides. Practically, we have some objective measures, like you see average key point distance and average Euclidean distance. And our method is working, it's better than the state of the art. And also we have had some user study, right? So practically, so we are comparing here with X2Face, and this is a proportion of time our method was preferred to X2Face for different data sets. So if you look into the papers, we have a lot of details also for the pose estimation part.
Okay, nice. And I was wondering about, did you consider your pose as a condition for your model for generating a new video with the same pose with different images?
I did not really understand your question because it was scattered. Can you say it again?
Did you consider your pose as a condition for your model?
Well, so the constraint was given, so if you talk about the second topic, the constraint was given by the target pose. So practically you need to provide a target pose, and then practically you are generating the appearance of your input image into the target pose. So that's a constraint you need.
Okay, I got it. Thank you so much. Thank you.
Thank you very much. There was, I think, also a hand raised from Ahmad. Ahmad, do you want to ask something, or was by accident? Okay. So thank you very much, Nico, for the very interesting presentation. And we go on with the next one. So Vasilis, if you can start sharing your your slides. Okay, very nice. Dr. Vasilis Migdalis is from Aristotle University of Thessaloniki. He's a research associate in the university, where he also did his studies and his PhD. His research interests are in computer vision and machine learning. And the talk of the presentation today will be adversarial face de-identification for privacy protection. So, okay, Vasil is very nice. We can see your slides. If you want to switch on your camera as well, it's up to you. But we cannot hear you. Maybe you are muted or... No, you're not muted, but we cannot hear you. So, Vasilis, can you try again with the microphone? Maybe change which microphone to be used from the settings.
Exactly, I'm trying.
Yes, we could hear you for a while. We can also see you now. But now we cannot hear you again. For a moment, we could hear you.
Okay, what about now?
Yes. Now very.
Okay, that's perfect.
Okay, thank you very much.
Okay, that's perfect. Sorry for this.
No problem.
So, hello, this is Vasilis Migdalis. I'm a postdoc researcher in Aristotle University of Thessaloniki, and this presentation is titled Adversarial Face De-Identification for Privacy Protection. It will overview the face de-identification problem, focusing on adversarial-based methods that disable automated face detection recognition in a humanly imperceptible manner, thus producing machine de-identified images that maintain maximal utility. When we perform face de-identification, we might actually refer to different engineering problems. Traditionally, the identification against humans was performed in media applications such as in the news, where they would apply some basic image processing technique for adding noise, like darkening, blurring, or pixelation, or even destroy the facial image region. The identification methods might target both machines and humans, using additive noise methods, reconstruction-based methods, or even generative methods. And in the case of adversarial attacks, we consider that these methods will only target machines, where the human will still be able to identify a person, but the machine cannot. Another identification problem is face detection hindering, which is a different application scenario where the detection recognition is treated as a unified pipeline, where automated face detection is the preliminary step. In essence, the basic assumption is that the recognizer will not work unless it is fed correctly detected facial images. This problem has different engineering variants as well. For example, the detector might be confused, so it will detect too many faces, or it may classify faces as other objects. For example, it will detect faces, but it will think that they will be cats, for example. Or another type of attack is that the detector will not detect faces at all. The simple definition of the de-identification problem is the following. Alter the image X with one that cannot be recognized by a function f. More formally, let X be a vector representation of the facial image Roy, having a label Y from a set C. Privacy protection is the problem of manipulating the input vector X by some technique such as additive noise, an affine transformation, or even a generative function so that the classifier is strict. That is, f of the xp is now not equal to y, where y is its original label. Common de-identification metrics include the so-called de-identification performance, which is a metric linked with the machine's classification accuracy. This metric is also applied subjectively for measuring the identification performance against humans, if required. The second important type of metrics are the similarity of the produced images with the original images, which is linked with the amount of noise introduced by the technique. We would want the noise to be low for maximal image utility. And finally, we can also employ some other type of metrics, subjective ones, such as faceness, image quality, etc., perceived image quality, etc. Traditional privacy protection in face recognition meant applying standard image processing techniques, such as blurring, reconstructions, etc., to produce XP. As can be seen in the examples on the right, on top we have a blurred image, and below there's an image produced by a reconstruction method. Although such techniques are simple, they are suboptimal against deep neural networks or even human identifiers. More recent methods are based on deep learning. For instance, neural network autoencoders or GANs. For the autoencoder case, an image dataset is employed to train an encoder-decoder architecture. The reconstructed image is produced using low-dimensional features extracted from the encoder. The network, therefore, produces a lossy reconstruction for a given image X, and this loss of information is enough to hinder face recognition accuracy. This approach has been extended in multi-label face recognition datasets, where the reconstruction is conditioned by a parameter vector that encodes multi-class properties. This allows including non-discriminating properties, for example, race, gender, in the reconstruction, while selectively hide other properties such as identity or age. Example results from the neural network autoencoder are shown here. The first row shows the original images, the second row shows images reconstructed by a standard autoencoder, and the final row shows images reconstructed by a method that was developed actually in AUTH, the supervised attribute preserving the identification. GAN-based de-identification employs a generator-discriminator network pair. One example is to employ domain adaptation techniques. That is, given an input image X and a target image Y, the network is trained to minimize the discrepancy of these two images in order to align the output into the distribution of the target image. A binary discriminator ensures that the outputs of the network belong in the same distribution as the target image. This pipeline leads to even more realistic image generations when compared to autoencoder-based identification, as shown in this slide. Here we see two state-of-the-art example methods using GAN-based image-to-image translation. And now we reach to the main subject of this lecture, which is the adversarial phase de-identification. This method family performs the identification by applying adversarial attacks on trained dupe neural network face recognizers. Thus, they require a face recognizer network and an example image. Adversarial attacks may be targeted or untargeted, white box or black box, iterative or single step, and we will talk about these properties in the next slides. They also might be transferable between different neural network architectures or classification methods. In every case, the de-identified image is produced by returning gradients from a trained neural network to the input directly. They generally produce imperceptible perturbations for humans. Targeted adversarial attacks for a given image X and a target label T that is obviously different than Y, targeted adversarial attacks solve the following optimization problem. They would minimize a vector P, that would be the noise added to the input image, subject to that the output image will now look like will be classified on class T instead of Y. And of course, XP must stay in the distribution of the original image. An additional stopping condition could be that we just want that the sample XP is misclassified. Solving the original adversarial attack problem would just need to minimize P over Fx that is not equal to Y. This optimization problem cannot be solved. So this is why we need a target label to guide the optimization problem towards a solution that is possible to be found. So let's go to the next slide. So the iterative fast gradient value method assuming a common neural network transform, let image samples X with pixel values normalized in the 0.1 domain, which is common when using a PyTorch framework, for example. The gradient descent update equations of iterative fast gradient value method are of the following form. So we take in each step the gradient of a loss function, the loss for classifying XP to label T, and take one step towards this direction. If we set A high enough, we might achieve an attack that will change the label directly. So this would be a one-step attack. Or we can do it in an iterative fashion. The fast gradient sign method is similar to the value method, but instead of applying the gradient values, it only applies the gradient signs multiplied by a variable A. In Aristotle, we have developed another method that is similar to the fast gradient value method, only by adding a realism loss term in the objective function. The gradient descent update equations are the same with fast gradient value method, but we add an additional term on the right, which is an L1 distance loss term, combined with a parameter lambda. The results of this work show that adversarial attacks produce extremely imperceptible changes to the original image. Humans cannot even spot the differences between adversarial images and the original images. However, neural networks cannot classify them correctly. As we can see, we can achieve even 99.6% the identification performance with images that look almost exactly like the input images. Another method that was developed in Aristotle University of Thessaloniki is an adversarial attack inspired by k-anonymity. K-anonymity concept was originally introduced by other research areas, like databases, where in field structured data, the k-anonymity concept is the following. It is assumed that an individual table record, for example, the record ID, may be identified by unique combinations of otherwise non-distinguishable attribute tuples, like sex, weight, age. These are the so-called quasi identifiers. Thus, dataset anonymization methods adhering to k-anonymity principles mask the appropriate attributes, the table columns that act as quasi identifiers, so that the remainder unique data combinations cannot be narrowed down to less than k combinations. That is, the maximum probability of identifying unique individuals cannot exceed 1 divided by k. In k-anonymity inspired adversarial attack, the concept has been altered as follows. The maximum probability of retrieving the real identity of its subject must be less than 1 divided by k in every possible classifier output ranking position. Formally, the neural network classifier label output is produced by finding the arguments of the maxima of the final classification layer, where G of x contain the network activations corresponding to the number of classes supported by the model. We have observed that adversarial samples could be classified correctly if, instead of taking the arguments of the maxima, we take the second maxima.
Still sorry for the interruption. If we can wrap up in 2-3 minutes.
Yes, okay. I have another 10 slides, maybe, but they will be fast.
Yes, please.
Okay. So, let me go forward. So, for example, if we need that the classifier output has less probability of 1 divided by k in every ranking position, then the adversarial sample is properly anonymized. So, to solve this optimization problem, we proposed the following optimization function, where on the left we have a similarity loss function that guides the adversarial sample to be close to the original image, and then we would need it that instead of moving closer to target class T, it will take the gradient towards every direction of k different possible classes. So that leads to, as if we compare it with the other adversarial attacks, that the k-anonymity inspired attacks that are with the green and blue are less probable to be classified correctly. For example, one can easily detect adversarial attacks. If an adversarial attack is detected, then you can use the classifier's second output position instead of the first to obtain the real label of the sample. With k-anonymity attacks, this is not possible. So as can be seen, the noise is imperceptible in almost every adversarial attack case. And to sum up, adversarial attacks minimally intervene with the original data, focusing only against automated analysis tools. Up to date, they are imperceptible by humans. It's also a great tool for examining robustness of neural networks. They have the potential of fooling multiple neural network architectures at the same time, using the transferability property. And they expose AI weaknesses in critical applications such as biometrics, traffic sign classification, etc. The limitations of adversarial attacks is that they require a host pre-trained network to generate the perturbations, and they are derived from it. So adversarial attacks are network specific, comes with no guarantee, and cannot be applied universally for the identification purposes, even though some attacks may be transferable between different architectures. Adversarial attacks provide no privacy protection against humans, thus will never become GDPR compliant. And finally, assuming that the adversarial robustness problem is solved in the future, adversarial attacks will not even work, or at least not that well. They will generate too much noise to fail completely. So this was it.
Okay, thank you very much. Very interesting and research work and application. Are there any questions? You can raise your hand in participant list, comment on Facebook, or just open your microphone. Okay, no question, Vasilis. Can you please elaborate a little bit on this generalization issue that they work, you mentioned, for specific architectures, so they can fool specific architectures, but others can still classify correctly? What is
actually, there's a problem of the generic de-identification, where someone would need to fool a range of networks. For example, if you want to fool both Facebook's network classifier and Google's. Adversarial attacks are usually transferable only with two similar architectures. For example, if you use a ResNet network for generating the adversarial attacks, then it can fool other ResNet architectures, even though they have different output, even if they support different classification classes. For example, this is the transferability property.
I see. Do you see any solution or ideas towards addressing this?
Well, adversarial attacks are generally transferable, but the whole goal is to create images that are good enough for people to identify the person. But if the adversarial robustness problem is solved, for example, classifiers will no longer be susceptible to adversarial attacks, then adversarial attacks will generate more noise. So they cannot be used in social media applications, for example, for privacy protection, unless we have the network that, and we know that this is the network that the classifiers are.
Okay.
We need to have it as input, yes.
Okay, thank you very much. I don't see any other questions, and I'm very glad that actually I you can introduce Annalisa, because you are in a much closer from my side. Thank you very much for accepting our invitation and be one of our keynote speakers. So please, Akis.
Yes. I'm really happy to introduce Professor Luisa Bertoliva. Luisa is Associate Professor at the Department of Industrial Engineering at the University Federico II of Naples and the holder of the Italian habilitation for full professor. In the past, she has been visiting professor at the Friedrich Alexander University in Erlangen, and she's currently a visiting scientist at Google AI in San Francisco in the perception team. She is a very well-known researcher in the field for her work in multimedia forensics, and also a member of the team that created the very well-known face forensics and face forensics plus datasets. So, Luisa, thank you very much, and the floor is yours.
Thank you very much, Akis, for this presentation, and thank you, Ioannis and Akis, for this invitation. I'm very happy to be here. So I will essentially talk about challenges in the detection of synthetic media and deepfakes. And of course, I mean, in these recent years, there have been published really many deep learning-based approaches to detect GAN-generated images and also deepfake videos. And they can be really very much effective, especially on high-quality data. Also, Akis actually showed this, and when you have low-quality data or when you don't have the same manipulation in training and test, maybe it can be quite difficult. And so actually major challenges are robustness to possible post-processing operations, so like compression, but even resizing. So every time you actually upload a video or an image on a social network or even on YouTube, all the characteristics of the video or the image are changed, and normally they are almost low quality and are much smaller. And this is actually really a challenge because sometimes you train on a specific compression pipeline, but then you test on a different one. So not only changing the type of manipulation like Facebook or change of expression or other type of, or maybe you only change the speech of the actor. So I mean, you can have multiple type of, as also shown before, of manipulation on the face, but also different GAN architectures that generate the image. And so all the generalization and robustness are actually some major challenges. But in this presentation, I will focus on counterforensics. I will not talk about adversarial attacks, even if also adversarial attacks can be a problem. But I will actually talk about counterforensics, where an expert is actually aware of the specific detectors, not of the specific detectors, but how the forensic detector is working and on which type of cues the forensic detectors relies, and so tries to take some countermeasures. And in particular, I will talk about so the main focus is a strategy that tries to fool GAN forensic detector. So we will talk about generative adversarial network images, and we will focus on hidden artifacts. There are many papers and also considerations about the fact that current GAN images show some visual artifacts like, for example, lack of symmetry, or some blurring in some, or you can actually perceive that there is something strange in the image. But we think that technology really grows so fast, so we normally work on techniques that rely on hidden artifacts. Hidden artifacts are very powerful. They are normally related to the camera, to the sensor, and both hardware and software included in the camera. And we will show in this talk how camera-based fingerprints can be important to detect manipulation in images or videos, but the fact that synthetic media indeed present different type of fingerprints, which are called artificial fingerprints. And our objective is can we make a synthetic media that actually has very different characteristics with respect to a real image appear as it was taken by a camera? So we will try to fool a detector, but first let's see how these detectors work. Because only a very deep knowledge of how detectors work can actually help you to develop a solution that can fool the detector. Now, of course, we want to understand the limit of current detectors. This is the reason for which in research you always study forensics, but also counter-forensics, because it helps to understand weaknesses of current detectors, and so we can also improve them. Now, a real image is normally contains camera-related traces because of the process which is inside the camera. That includes, like there is of course a lens, there is some software like white balancing, demosaicing, brightness, gamma correction, and finally we have the last step of JPEG compression. And of course, all these operations are very specific of the specific camera. In particular, different type of camera models share different type of algorithms. So normally forensics and forgery detection is very much related to source and camera identification. And this type of traces which are hidden inside this specific software inside the camera, but also the hardware. Also the sensor carries some specific traces. I don't know if someone of you has actually worked or read something about PRNU, which is a very strong fingerprint that can be used for device identification. So, I mean, these are very important traces. They are hidden, so you cannot see them. So even if the image is perfect visually, they are present inside the image. And we recently proposed a way to extract these camera-based fingerprints because we thought that they were, I mean, there is a very large literature on this, but we actually proposed a way to do this using deep learning, and in particular training a science network. The network was actually trained using a lot of almost above 100 different camera models, and we extracted patches from these images, and our learning procedure was to minimize distance between patches from same camera and maximize the distance between patches from different cameras. In this way, we were able to extract a sort of fingerprint. Note that when we have a test image, our approach was actually trained on a separate number of cameras which are not present in test. So we just train it once and use it for all the test images. And we took care to not consider same images or same cameras models in training and test. I mean, we just use some publicly available data sets and some internal cameras just to increase the number of images for which we knew they were coming from a specific device. And then we used the trained model on all the test images. So there is actually a separation in training and test. This is quite important. Otherwise, you can actually obtain very polarized results. And this, we call this extracted fingerprint, which shows the artifacts of the cameras like a noise print, because I mean, it's like related also to the noise present inside the camera. And using a clustering procedure, we were able to identify anomalies which actually shows that there were some part of the image not consistent with the artifacts of the specific camera. And this type of approach was actually also extended to video. Here we show some preliminary results we presented last year, were applied especially on the deepfake and problem, but also face-to-face and face swapping, so other type of face manipulation, where we could actually extract this type of anomalies of manipulation inside the video. And here you can see actually in the noise print, you can see this also visually that there is something strange, especially on some type of manipulation. And we also applied it on a YouTube video where there was a face swapping between two actors. And you can see that there is actually a very strong fingerprint on the face. Now, of course, I mean, this was a very nice video to show this because it's not easy to train a deep network using many videos from different cameras, and this was actually in this moment our major limit for this approach. And okay, here it was just the clustering procedure in order to understand that there was that one phase was pristine and the other was forged. And just as an example, this was also applied on another YouTube video where there was in April, there was in 1st of April, there was actually a joke with, there was a video on the internet with an Amazon blimp delivering drones. Now there is no deepfakes here, it's a computer graphic based forgery, this blimp, but, it was in any case, it was in any case detected because the strength of these camera fingerprints is that they do not care about the type of manipulation. They just show up anomalies. So if I extract an anomaly with respect to the background, then I can detect this type of manipulation. Of course, it's a very small traces. I mean, the traces are very small. So if you compress a video very much and you have very low quality videos, then it's really hard. You need a much larger data set in order to train the approach. And so, I mean, we said, okay, but if these real images present this very strong camera fingerprint, do also synthetic images leave a sort of fingerprint? And this was a work carried out a couple of years ago during a challenge organized in Medifor, which was a project we joined, funded by DARPA, and where we were actually involved, and in the last 4 years. And so we examined a lot of synthetic images and wanted to understand if they presented some sort of specific artifacts that were related to the GAN architecture. And so we applied a procedure which was very much related to the way that the fingerprint is extracted in the classic paradigm of PRNU, of this photoresponse non-uniformity noise. So we considered a generator, and we took almost 300 GAN images. We could not really apply the same strategy we did on noise print because we didn't have at that time so large data sets with very different architectures. I mean, in noise print we used at the beginning a data set of 125 different camera models, and then after a data set of more than 600 camera models. But here we had very few different GAN architectures, and so we couldn't train a way to extract the fingerprint, and we just applied a very basic approach, which is a classical one, as I said before, in the forensics literature. So we took few hundreds of GAN images, then applied a denoiser. You can just use a standard or a wavelet-based denoiser is a standard one, but even a non-local based one, which is a bit better to extract noise and remove the scene content. Then average this noise residual and obtain this sort of fingerprint that then has to be compared with the test image by using a normalized cross correlation. Now, this was very effective during the challenge and helped us to obtain very good results. And we so wanted to try to better understand this. And we made an experiment using two different architectures, a cycle GAN and a progressive growing GAN, where these fingerprints were estimated using a growing number of images. You can see here from 2 till 512 images. And of course, if you just estimate using a low number of images, you have a lot of noise-like appearance of this fingerprint. But then using a certain number of images, the pattern seems to be a quasi-periodical pattern and approximate to what we call this artificial GAN fingerprint. And we also noted that these fingerprints were very much correlated to the specific architecture. In fact, here you can see that the correlations between these fingerprints of the same camera, the same GAN architecture and a different one actually are quite different, and you can discriminate them. So you can actually also carry out what is called attribution with respect to the specific GAN architecture. Now, starting from 2 years ago, there were a lot of study and works on these GAN-generated images, a lot of interest. And so there are many works. I mean, this is not exhaustive, but these are some of the works about artificial fingerprints in the spatial domain, but also in the frequency domain. Given that in a GAN architecture, you often have this upsampling operation that actually cause these peaks in the domain, in the frequency domain. And so you can actually notice that there are hidden traces. So we are not talking about visual traces, just they are hidden inside the images. Okay, so given that these forensic detectors are able to distinguish synthetic media from real images because of these specific artifacts, can we make something in order to fool the forensic detector and insert traces of a camera inside the synthetic image? Because of course a synthetic image has not been taken from a camera, from a real camera, and the real camera has these very strong traces. So can we do something in order to introduce these traces in the synthetic image so that the forensic detector is actually fooled by this type of approach? So we are not really working on trying to fool a specific forensic detector. We are just saying normally these detectors work well because they are based on these hidden traces inside, which are present inside real and synthetic images. Can we do something in order to fool them because we know that they are based on these traces? So it's a bit different with respect to the concept. I mean, of course, we are doing an attack, but it's not an adversarial attack in terms of adversarial perturbation as intended in the computer vision now. It's really a counter-forensic approach. So we know how the forensic detector works. They rely on this type of traces, and we want to fool them. So how to make a synthetic image appear like acquired by a real camera? This means that we need actually to insert the specific camera traces of a natural image. And this is actually our objective. The scenario is that we want, of course, we don't want to change the semantic content. So in the perturbation we are introducing, the artifacts we are introducing should not be visible, so no visible distortion. And we do not have any information about the GAN architecture used for generation or the GAN detector. But we're supposed to have a certain number of training images drawn from the same distribution. So we need to have synthetic images from different GAN images that were also actually used for training a GAN detector. Okay, so we have a synthetic and real image, and our approach try actually to generate a spoof image where we insert these camera traces. So the generator introduces these camera traces, but it has also to preserve the semantic content. And so in this respect, we use a combination of an objective distortion, which actually measure, and also a perceptual loss, of course. And after the generator, there is also a discriminator. What is interesting of our approach is that, of course, the discriminator has to distinguish from real, from generated images, but we also want that the discriminator is actually able to generate an image that has to be different from a synthetic image. It doesn't have to possess the specific characteristic of a GAN image. Otherwise, of course, I mean, the approach is not working well. And finally, there is an embedder. This embedder was quite important in our analysis when we did our ablation study, in the sense that we have an embedder that tries to extract important characteristics of the camera. It was trained just once. It was pre-trained using a very large number of different cameras in order to have to generate a feature of vector from these cameras. And so the generator has not only to fool the discriminator, but it has also to fool the embedder. And so this actually means that we need to ensure that the features vector extracted from the attacked images are actually similar to the ones that are generated by this embedder from real images. So, I mean, we are trying to do a lot of possible strategies in order to remove all the possible synthetic traces and insert the real traces. The available data, so for training, we used 400 images of a target camera. We have a targeted attack because we insert traces of a specific camera. I mean, we actually do not care which type of camera. We just want, because we want to fool a GAN detector. And we use different architectures. Here there are some reference star GAN, cycle GAN, progressive growing GAN, style GAN, rare GAN. And the embedder training, we used a very large collection of 600 camera models in order actually to have this very large number of images coming from different camera models. And then we also used as test images, not only images coming from same architectures, but also an architecture that was not used for training, which is this big GAN, an out-of-training architecture. So you can see here that the attacked images are actually identical visually to the synthetic ones. So also we don't have to perceive that there is a difference. And here we considered, this was a work carried out last year, and then we made some other experiments a few months ago. So we just took some state-of-the-art detectors, and in particular this approach, which was very interesting about the artifacts in the frequency domain. And here you can see that the true positive rate is very high. I mean, for all the architectures present in training, except the one which was not present in test. Okay, here we show this problem of generalization even for GAN detection. And then after our attack, you can see that the true positive rate actually goes down for all the architectures. I mean, actually the out of training is a bit better, but I mean, you can see you are 100% and then you goes down to 2.5, 2.8, or even very, very low numbers. And we repeated this also for an approach we proposed a couple of years ago, which is a classic supervised learning. And also here, I mean, the approach is very good. It is not actually, it's, okay, sorry, I mean, there was not, there was a problem here in the bar for beacon. Okay, this is the correct one. And here you can see that here there was also a bit of robustness with respect to an architecture which was out of the training set, but after our attack, even in this case, true positive rate goes very much down. So, I mean, it's quite a problem. Then we applied it to a recent paper proposed at CPR this year. And also here, the performance are very good before the attack, and then they get worse after, even if this approach is actually better than the others. And the idea of this approach was to carry out a very strong augmentation. As also Akis highlighted before, if you want to gain robustness, you really need to have this very strong augmentation strategy in training. So we repeated the experiment using augmentation also for the other approaches, but in any case, the performance decreases, and actually also in this case. So, I mean, of course, I mean, there are some architectures for which there is performance are better, but in general, I mean, it's a bit of a problem if you have an architecture which was not present in training. Here we also conducted a study changing the quality of the image, and you can see that if the quality of the image is worse, then actually the attack is also not very much successful. This is almost in line with some of the experiments we carried out using just some standard adversarial attacks. We noticed that adversarial attacks is quite effective, but if you compress the data, which is very much a realistic scenario, then compression actually reduces the strength of the attack. And this was also quite important to take into account in a realistic scenario. Okay, so final consideration. So we actually made this, developed this approach in order to understand weaknesses of current detectors and injected these camera traces to full to full GAN detectors. This actually also full camera model identification techniques. I didn't show in this slides, but there are results in the paper. A strong limitation is actually that these traces are not really reproducing a spatial fingerprint. So it's not really a noise print we are inserting inside. It's just, there are just some traces inside the image, but it's not a spatial fingerprint. So, I mean, it would be interesting to understand what happens if we try to extract it after. And okay, but the most important thing to say is, okay, we need to develop reliable forensic detectors, which I think is really hard. It's really hard because of different problems. Because of low quality data, as at the beginning we said, because of new attacks, new unseen attacks, and new manipulations that actually came out with new technology, and also because a skilled attacker can know the principles of these forensic detectors and can actually apply very strong attacks in order to fool these detectors, even without the knowledge of the specific detector, so in a sort of black box scenario. Okay, these are some references, especially for the GAN generation data I showed you before. And just want to thank all the other people working in my team, both from Naples and also from the Technical University of Munich. And we have a collaboration with the computer vision group of Matthias, the visual computing group of Matthias Nisser. And I also want to thank DARPA and Google for supporting our research. So thank you. I'm here open for possible questions.
Yes, so please, if there are any questions, you can raise your hand or just switch on your microphone and pose the question directly.
Okay, there was a question about research funded by DARPA. So DARPA actually, there was in 2016, the MEDI4 program, and we were actually involved in this program from 2016 to till now, to 2020. And now there is actually another one, it's called Semaphore, Semantics Forensics, and I'm also involved in this project.
Okay, yes, thank you very much. Yes, Akis has raised his hand, yes, of course.
Yes, thank you very much. It was really a very valuable talk. I wonder, there is a kind of an ethical dilemma that researchers working in this area face. On the one hand, they really want to share their results and outcomes, and also to make their research reproducible. But at the same time, revealing this knowledge gives an advantage to adversaries.
Yeah, you're right. But I mean, I think it doesn't work if you hide them. In the sense, you're perfectly right, because there are a lot of concern about this, like also the data. I mean, all this data that we use to train the detectors, they are available to everybody. And so, of course, you can also do better in terms of counter forensics or in terms of possible new, I mean, we saw the presentations by Nick, which was a great presentation about how you can do very well. And of course, I mean, it doesn't work in any case if you hide the approaches, in the sense that this does not mean that the attacker does not have this knowledge or cannot take the knowledge by using the technology, also because this technology is so much important in a lot of different areas. I mean, it is important for data augmentation, but it is also important in movie production and video games, and there are many interesting applications. So I understand, Akis, your concern. I mean, it was also a concern about in our community, and there are some research groups that actually do not share, but there are other who actually share. So, I mean, it's complicated because if you say don't share, nobody will share. I mean, it should be like, otherwise it really doesn't work, unfortunately. I mean, it's complicated.
Yes, yes.
It has been always like this in forensics. I mean, I started in forensics almost 10 years ago, and this was actually always a concern about how should you open about data and algorithm, of course. But if you want to hide something, everybody should do this. Otherwise, of course, and we do research, and we also need to share, and in order to understand even challenges and all this data, really advance a lot the research, and it's so important. So, I mean, it's a bit complicated. You're right, however.
Indeed. Are there any other questions or comments? Okay, there is a question in the chat. How can we deal with mode collapse during training the GAN? Mode collapse.
In the sense that, in our case, we do not really, we are not really affected by this, in the sense that we are not generating new type of images, and so we are not, we have not the constraint of trying to make an image as much as real as possible. So in our case, I mean, we didn't have this specific problem. We're just training a GAN in order to insert the faces of the camera, which were completely hidden, as you have seen. I mean, there were no, it was not something visual. So we didn't have really a constraint on the appearance of the product, of the final generated image. Maybe for people working on the GAN generation, this can be a more interesting point to discuss.
Okay, thank you very much. Any other questions, either directly or through the chat? Let me also check Facebook for a moment. Okay, nothing there as well. So, Luisa, thank you very much for this very interesting
thank you again.
talk. I think this is the end of the workshop as well. I would like to thank everybody for the participation. There were more than 100 participants, also taking into account the Facebook Live, 100 or 150 participants all the time. I would like to thank the speakers for the excellent presentations. I think we covered an important topic quite well, from overview presentations to applications in various areas, from media production to deepfakes, and then how to address these issues with synthetically generated content, either in deepfakes, in forensics, or on privacy preserving in face detection. Please follow the website of the event in the following days. We are going to upload the presentations, which can be made available, links to the recording, and you can follow the AI4Media activities in Twitter. in order to be informed for any other future events, activities, results, and so on. We will be glad to let you know about all this. So I hope you enjoyed the workshop, you found it useful. Thank you all again, and have a nice evening.
Bye-bye. Thank you.
Bye. Bye.
Bye.
Bye.
Bye-bye.
Thank you, bye.
Thank you. Bye. Bye.